We've landed robots on Mars. We've sent spacecraft to the very edge of the solar system. We've even touched the sun. We think we're getting pretty good at this. Then you look up at the nearest star, just 4 light years away, and that confidence evaporates instantly. But forget 4 light years. Let's be humble and talk about just 1 single light year. How far is it, and what would it actually take to cross it? If you're someone who genuinely wants to understand the universe at a deeper level, make sure to give this video a like. Now let's get started. A light year is not a measure of time, it's a measure of distance. Specifically, it's the distance that light covers in 1 full year of travel. And when you actually sit down and do the calculation, you get a number so large it almost loses meaning. Approximately 9.4 trillion kilometers. Write that out and you get 9 followed by 12 zeros, then some change. 9.46 trillion kilometers. Now your brain is going to try to file that number away as very far. But let's be honest, your brain has no real framework for that. So let's try something different. Let's build the scale from the ground up, using things you can actually picture. The distance from Earth to the Moon is about 384,000 kilometers. That already feels enormous. It took the Apollo astronauts roughly 3 days to get there, and that was considered one of humanity's greatest achievements. Now multiply that moon distance by about 24 million. That's 1 light year. 24 million trips to the moon, back to back, in a straight line. Still struggling to feel it? Let's try again. The Sun is about 150 million kilometers away from Earth. That distance, which we call 1 astronomical unit, is the foundational unit astronomers use to measure things in our solar system. 1 light year is equal to about 63,000 astronomical units, 63,000 times the distance from the Earth to the Sun, in one direction, in a straight line. If you drove a car at 100 kilometers per hour, no stops, no sleep, just pure continuous driving, it would take you over 10 billion years to cover 1 light year. The universe itself is only about 13.8 billion years old. You would need almost the entire age of the cosmos just to drive across 1 light year of space in a car. And there are stars out there thousands of light years away, tens of thousands, hundreds of thousands. The Milky Way alone stretches roughly 100,000 light years from one side to the other, which actually raises a question that goes even deeper than today's topic. If 1 light year is this incomprehensible, what would it take to cross the entire galaxy? We actually did a full breakdown of that in another video on the card above. We explore how long it would really take us to leave the Milky Way. I highly recommend watching it after this one, because the 2 topics connect in ways that will blow your mind. Link is in the description and pinned on the comments. But back to our 1 light year, we've established the distance. Now let's talk about what actually getting there would require. Here's where it gets interesting, and where most people's intuition completely breaks down. When we talk about traveling 1 light year, we're not just talking about covering a distance. We're talking about surviving a journey that would last longer than all of recorded human history, potentially many times over, depending on how fast you're going. And speed, as it turns out, is the central problem, not just practically but physically, because the universe has rules, very strict, very mathematical, very unforgiving rules about how fast things can move and what happens to them when they try to push those limits. Let's start with where human technology actually stands right now, in the mid-2020s, not in science fiction, not in theoretical physics papers. Right now, in reality, the fastest propulsion systems humans have ever engineered, things like ion drives, which use electric fields to accelerate ions and produce thrust, can push a vessel to remarkable speeds over long periods of time. The Dawn mission, launched in 2007, used ion propulsion, and reach speeds of around 40,000 kilometers per hour relative to Earth at its peak. That's fast by everyday human standards. Shockingly, breathtakingly fast compared to anything we experience on the ground. And yet, at 40,000 kilometers per hour, traveling 1 light year would take you approximately 26,000 years. Not 26,000 days, not 26,000 months, 26,000 years. To put that in perspective, 26,000 years ago, humans were still in the Stone Age. Woolly mammoths were still walking the earth. The Sahara Desert hadn't even dried out yet. It was green and dotted with lakes. Anatomically modern humans had been around for a while, but the concept of agriculture was still about 15,000 years away. That's the journey. That's how far 1 light year is, measured in human time, using some of the best propulsion we've ever built. Now, you might be thinking, okay, but surely we can do better than that. Surely we can go faster. And yes, in theory we can. But every step toward going faster introduces new layers of complexity that are almost as hard to wrap your head around as the distances itself. Let's talk about what faster even looks like on a cosmic scale. The fastest natural objects in our galaxy, aside from particles like that, oh my god, cosmic ray, are hypervelocity stars. These are stars that have been flung out of the galactic center at extraordinary speeds, sometimes through gravitational interactions near the supermassive black hole at the heart of the Milky Way. The first confirmed hypervelocity star, catalogued as HVS-1, was discovered in 2005. It was screaming away from the galactic center at roughly 670 kilometers per second. That's about 2.4 million kilometers per hour. An entire star moving at 2.4 million kilometers per hour. At that speed, the speed of a hypervelocity star traveling 1 light year would still take you approximately 1,600 years. Still longer than the entire span of time since the fall of Rome. Still longer than the age of Islam, of the Aztec Empire, of the Renaissance, of the Industrial Revolution, all of it combined twice over. 1 light year, 1,600 years, even if you could somehow move like a hypervelocity star. This is the moment where the scale of space stops being a statistic and starts becoming something you feel in your chest. And we haven't even started talking about what this journey would do to the human body. Because here's the thing, distance and time are only part of the problem. The deeper you go into what this trip would actually require, the more you realize that physics isn't just indifferent to your survival. In some ways, it seems almost actively hostile to it, but that's exactly what we're going to dig into next. What would actually happen to you on a journey of 1 light year? What does your body face? What does your mind face? And is there any version of physics, any path, any loophole, any theoretical framework that makes this journey survivable in a human lifetime? Stay with me, because what comes next is where this goes from fascinating to genuinely mind-bending. Let's talk about your body for a moment, not your ambitions, not your technology, your actual, physical, biological body, the thing that has to survive this trip, because here's what most space content glosses over. The universe doesn't care about your dreams. It operates on physics, chemistry, and biology. And all three of those systems have hard limits that no amount of engineering enthusiasm can simply wish away. If you're going to seriously ask how long it would take a human being to travel 1 light year, you have to seriously reckon with what that journey does to the person inside the ship. And the first thing it does, even before you've left the solar system, is try to kill you with radiation. Space is not empty. This is one of those things that sounds obvious when you say it out loud, but its implications are staggering. The space between stars is filled with a constant rain of high-energy particles, protons, atomic nuclei, electrons, collectively known as galactic cosmic rays. These aren't the gentle ultraviolet rays you put sunscreen on for. These are particles moving at a significant fraction of the speed of light, carrying enough energy to punch straight through the hull of a spacecraft and straight through your body. On Earth, you're protected by two things: the planet's magnetic field and the thick blanket of atmosphere above you. Together, they absorb and deflect the vast majority of these particles before they ever reach you. In deep space, you have neither of those shields. You're exposed completely. NASA has been studying this problem intensively in the context of a crewed mission to Mars, which would only last somewhere between 6 and 30 months depending on the mission profile. And even for that relatively short journey, the radiation exposure is a serious concern. Astronauts on the International Space Station, which sits within Earth's protective magnetic bubble, receive about 10 times more radiation than people on the ground. On a mission to Mars, that number jumps dramatically, and a trip lasting thousands of years to cover 1 light year. The cumulative radiation dose would be lethal many times over, not once, not twice, but orders of magnitude beyond any survivable threshold without extraordinary shielding or some technology we haven't invented yet. And shielding itself is a problem, because the most effective shielding against galactic cosmic rays is mass. You need dense material, water, polyethylene, lead, between you and the radiation, but mass is the enemy of speed in space travel. Every kilogram you add to a spacecraft makes it harder to accelerate, requires more fuel, and makes the already impossible problem of reaching meaningful velocities even more impossible. It's a brutal engineering paradox. The thing that keeps you alive makes it harder to go fast, and going faster means you need to survive longer in transit, which means you need more shielding, which slows you down further. It's like trying to run a marathon while carrying the weight of everything you'd need to survive the marathon. But radiation is only the beginning. Let's talk about what happens to the human body in prolonged microgravity, because a journey of any serious length is going to involve spending a very, very long time weightless. The International Space Station has given us the most detailed picture we have of what extended microgravity does to a person. Astronauts on 6-month missions, which is considered a long-duration stay, come back with measurable bone density loss, muscle atrophy, fluid shifts in the body that change the shape of the eyeball and affect vision, and cardiovascular changes that take weeks or months to reverse. The body, in other words, adapts to weightlessness in ways that are actively harmful when you return to gravity. Russian cosmonaut Valery Polyakov holds the record for the longest single spaceflight, spending 437 days aboard the Mir space station from 1994 to 1995. When he landed, he could walk, which was remarkable, but his body had been profoundly reshaped by more than a year in microgravity, and that was 437 days. A trip to cover 1 light year at even the most optimistic realistic speeds would last not days, not months, but generations. This is the point where the individual human journey becomes something else entirely. It stops being a trip and starts being a civilization. If you were to send humans on a ship capable of traveling at, say, 1/10 of the speed of light, which is roughly 30,000 kilometers per second, and which would require propulsion technology far beyond anything we currently possess, the journey would still take about 10 years. 10 years of continuous exposure to radiation, microgravity, cosmic isolation, psychological strain, and the complete absence of any kind of rescue or resupply. 10 years is survivable, in principle. But achieving 1/10 of the speed of light requires energy on a scale that is genuinely difficult to even describe. Here's a way to think about it. The kinetic energy of an object increases with the square of its velocity. Double your speed, and you need 4 times the energy. Triple your speed, and you need 9 times the energy. Push toward a significant fraction of the speed of light, and the energy requirements become almost cosmically absurd. To accelerate a spacecraft of even a modest mass, say 1,000 kilograms, which is smaller than a family car, to 1/10 of the speed of light, you would need energy roughly equivalent to the entire global electricity consumption of Earth for about 800 years. 8 centuries of all the power every human on the planet uses just to get one small object to 1/10 light speed. And then you have to slow down at the other end, because arriving at 1 light year's distance at 1/10 the speed of light and having no way to decelerate means you just fly past your destination and keep going forever into the void. Deceleration requires the same energy as acceleration, so double everything. 1,600 years of global electricity production just to send something the size of a small car 1 light year and stop it at the destination. Now you start to feel it. Not just the distance, but the energy desert that surrounds it. Space isn't just big. It's energetically prohibitive in a way that makes our current civilization look like a candle trying to illuminate a continent. But here's where it gets philosophically interesting, and this is the part I want you to really sit with for a moment. Everything we've talked about so far assumes that the laws of physics as we currently understand them are fixed, that the speed of light is an absolute wall, that energy requirements scale the way our equations say they do, that space is simply a passive backdrop through which you travel. But what if some of those assumptions are incomplete? Science, real science, not science fiction, is full of moments where a framework that seemed airtight turned out to have a crack in it. A crack that, once widened, completely changed the picture. Consider what happened with our understanding of the atom. For most of human history, the atom was considered the smallest indivisible unit of matter. The word itself comes from the Greek for uncuttable. Then we discovered the electron, then the nucleus, then protons and neutrons, then quarks. Each discovery didn't just add a layer to the picture, it completely reorganized the picture. The atom went from being the simplest possible thing to being a staggeringly complex structure with its own internal architecture, held together by forces that nobody had imagined existed. Our understanding of space and travel might be at a similar frontier right now, not because the physics is wrong, but because it might be incomplete. In 1994, a Mexican physicist named Miguel Alcubierre published a paper that sent ripples through the theoretical physics community. Working within the mathematical framework of general relativity, Einstein's own equations, Alcubierre described a geometry of space-time that would, in principle, allow a region of space to move faster than light. Not an object inside space, but space itself. The idea was to compress space in front of a spacecraft and expand it behind, creating a kind of wave that the ship would ride. Inside the bubble, the laws of physics remain perfectly normal. No acceleration, no relativistic effects, just a pocket of flat space-time being carried along like a surfer on a wave. The concept became known as the Alcubierre warp drive, and it is real physics, not science fiction, in the sense that it emerges directly from Einstein's equations. General relativity does not forbid it mathematically, but it comes with problems, enormous problems, the kind of problems that make the energy requirements we discussed earlier look manageable by comparison. To sustain an Alcubierre bubble of even a modest size, the original calculations suggested you would need negative energy, a quantity of exotic matter with negative mass energy, equivalent to the mass of a planet the size of Jupiter. Negative mass energy, something that, as far as we know, does not exist in nature in useful quantities. However, and this is the part that keeps physicists thinking, subsequent work has refined those calculations. In 2012, Harold White at NASA's Johnson Space Center published research suggesting that by modifying the geometry of the warp bubble, making it thinner, oscillating it, the energy requirements could be dramatically reduced, not to zero, not to anything we could build tomorrow, but potentially to something less cosmically impossible. The research is preliminary, the challenges are extraordinary, but the mathematical door has not been closed, and that matters, because in the history of science, mathematical doors that remain open have a habit of eventually being walked through. We are at the edge of what we know, and that edge, if you look at it the right way, is the most exciting place in the universe to stand. But let's pull back from the theoretical for a moment and return to something grounded, because there's a proposal that sits between what we can do today and warp drives that deserves serious attention. It's called laser sail propulsion, and some of the most respected scientists alive are betting real money and real effort on it. The Breakthrough Starshot Initiative, backed by the late Stephen Hawking, physicist Yuri Milner, and a coalition of scientists and investors, proposed something genuinely audacious: use an array of powerful, ground-based lasers to accelerate an extremely lightweight, sail-like spacecraft to a significant fraction of the speed of light, not a crude vessel, a tiny gram-scale chip carrying sensors and cameras attached to a sail made of materials thinner than a human hair, pushed by a laser array with a combined power of up to 100 gigawatts. The target of the original Breakthrough Starshot concept was Alpha Centauri, the nearest star system to our own, at roughly 4.2 light-years away. The projected travel time, at the proposed speed of about 20% of the speed of light, was approximately 20 years, for over 4 light-years of distance. That's not science fiction. That's a funded research program with a serious scientific team working on the engineering right now. The challenges are immense: maintaining laser focus across vast distances, building sails that can survive the launch acceleration, designing electronics small and hardy enough to function after the trip and transmit data back. But the physics is sound, and if you scale that concept, if you imagine a future where laser arrays are more powerful, where sails are more efficient, suddenly 1 light-year starts to look like something that could, in principle, be crossed in a handful of years for an uncrewed probe. Not a human, but something with our fingerprints on it. Something that carries our questions. That thought should do something to you, because it means we might be living in the generation, or within a few generations of the generation, that first sends something beyond the nearest stars, not a civilization that looked up at the sky and dreamed, a civilization that actually reached. And yet, and this is the tension I want to leave you sitting with as we head into the next section, reaching with a chip the size of a postage stamp is one thing. Reaching with a human being is something else entirely, because humans aren't just physical objects that need to survive a trip. Humans are psychological creatures, social creatures, creatures of meaning and memory and relationship. And what a journey of years or decades or centuries does to the human mind might be the hardest problem of all. What does isolation do to a person when the nearest other human is a light year away? What does it mean to make a decision on a ship when the people who sent you have been dead for centuries? What does it feel like to be the most alone any human being has ever been, by a margin so vast it makes all previous loneliness look like a crowd? That's what we're stepping into next, and it's going to change the way you think about this journey entirely. If you are enjoying this journey, make sure to give this video a like and subscribe. Every video on this channel is built to give you that feeling. There's a psychological experiment that has never been officially run and probably never will be, because the ethics of it are simply too dark to approve. But the thought experiment itself is worth sitting with, because it gets at something that no engineering blueprint, no propulsion study, no materials science paper has ever fully addressed. Imagine you put a person in a room. The room is comfortable, climate-controlled, well lit, stocked with food, water, books, music, films, everything they might need to stay physically healthy and mentally stimulated. And then you seal the door, not for a day, not for a week, for years, with no contact with the outside world, no conversations with other human beings, no sense of progress, no horizon, no sunrise, no birdsong, just the room, just the hum of recycled air, just the person. How long before the mind begins to fracture? We don't need to speculate entirely, because we have data, imperfect, incomplete but real, solitary confinement studies, polar expedition research, submarine crew psychology, and the extensive work done by space agencies studying isolation and confinement all point to the same conclusion. The human mind is not built for profound, sustained loneliness. It needs stimulation, connection, variety, and a sense of forward movement through time that is anchored in shared reality with other people. The Mars 500 experiment, conducted in Moscow between 2010 and 2011, locked 6 volunteers in a simulated spacecraft for 520 days, roughly the duration of a round trip to Mars. They had communication with the outside world, albeit with simulated delays. They had tasks, routines, and structure. And even under those relatively controlled, relatively supported conditions, the crew experienced significant psychological strain. Sleep disorders became common. Physical activity dropped dramatically. Some crew members showed signs of depression. The psychological load of confinement, even with communication and purpose, was heavy enough to be measurable and concerning. Now scale that up. Not 520 days, not even 5 years. Imagine a journey lasting decades, or, if you're using slower but more realistic propulsion, centuries. Even the most optimistic, crude mission scenarios involving a single human lifetime would require someone to spend the majority of their waking existence in a sealed environment, cut off from the living world, moving through a darkness so absolute that the nearest light source, the star they left behind, would shrink to just another point in the sky within a few years. The psychological architecture of a light-year journey isn't just a footnote, it might be the central challenge, and it raises a question that philosophers and scientists are only just beginning to take seriously. What does a multi-generational mission do to the people born into it? Because here's the reality. If you're traveling at speeds that would take centuries to cover 1 light year, the people who arrive at the destination are not the people who left, not even close. The original crew would be long dead, their children would be dead, possibly their grandchildren. The individuals who finally decelerate and look out the window at their destination would be the descendants, many generations removed, of the humans who made the original choice to go. They didn't choose this. They were born into it, born into a ship, born into a mission, born into a life whose entire geography is metal walls and recycled air and the faint, philosophical promise that one day, long after they too are gone, someone carrying their genes will arrive somewhere meaningful. This concept has a name in the scientific and philosophical literature. It's called the generation ship problem, or in its more poetic framing, the world ship dilemma. And it's not purely theoretical, it's been seriously studied by researchers in fields ranging from genetics to sociology to ethics, because if we're ever going to send humans beyond the nearest stars, we have to confront it directly. The genetic dimension alone is staggering. A small founding population, say, a few hundred or a few thousand people, carries only a fraction of the genetic diversity of the broader human species. Over generations of breeding within that closed group, the risks of inbreeding, genetic drift, and the expression of recessive disorders increase. Population geneticists have tried to calculate the minimum viable founding population for a multi-generational space mission, the number of people you'd need to maintain sufficient genetic health across the centuries of travel. Estimates vary, But some studies suggest you'd need somewhere between 10,000 and 40,000 individuals to maintain robust genetic diversity across a journey of several centuries. 10,000 to 40,000 people on a ship for centuries. That's not a spacecraft, that's a city, a floating, self-sustaining city carrying enough genetic, cultural, and social complexity to remain coherent as a civilization across generations that will never see a planet, never feel rain, never hear wind, never experience any of the things that shape the psychology of the species that built the ship in the first place. What kind of culture emerges from that? What kind of religion, art, politics, social structure? What happens when some members of the 5th or 8th or 12th generation decide they don't believe in the mission anymore? What happens when a faction within the ship argues that turning around, even though the point of no return past a century ago, is the morally correct thing to do? These questions sound like science fiction. They are not. They are the legitimate downstream consequences of taking the physics of light-year travel seriously. They are what responsible science has to grapple with if it's going to advocate for human expansion beyond the solar system. And here's where it gets even more philosophically complex, because there's another layer to this that most people don't think about, even if you somehow solved every engineering problem. Even if you built a ship with perfect shielding, abundant energy, artificial gravity to prevent bone loss, and a founding population large enough to maintain genetic diversity, even if you achieved all of that, the moment you left the solar system, you would be entering a communication desert unlike anything humans have ever experienced. Right now, our best long-distance space communication relies on radio waves. Radio waves travel at the speed of light, which means they're the fastest signal we can send. But light speed, as we've established, is not fast on the scale of even 1 light year. A message sent from the ship back to Earth, or from Earth to the ship, would take 1 year to arrive, 1 full year. If the crew encountered a problem and radioed for help or advice, the earliest they could receive a response would be 2 years later. And that's assuming the people on Earth could even help, which becomes increasingly unlikely as the ship ventures into entirely unknown territory. The crew would be, in every meaningful sense, on their own, not just physically, not just geographically, epistemologically. They would be making decisions, life and death decisions, civilization-level decisions, without any possibility of consulting the civilization that sent them. Earth would become, within a generation, a philosophical abstraction, a story the elders told, a blue dot that even the most powerful onboard telescope would eventually struggle to distinguish from the surrounding stars. And yet, and this is the part that genuinely moves me, this has always been true of human exploration. Every sailor who pushed past the horizon into unknown ocean, every tribe that crossed a land bridge into an unmapped continent, every individual who walked away from the known world into the dark, they all faced their own version of this, a point of no return. A moment where the familiar world fell below the horizon and all that remained was forward. We are a species of horizon crossers. It's in the deep structure of who we are. And knowing that, really feeling it, changes the nature of this question, because it means the question isn't just how long would it take. The question is also, what kind of people would it take? What kind of courage, what kind of commitment, what kind of love for the unknown would drive a human being, or a community of human beings, to willingly step into a journey measured not in years but in lifetimes? The answer, I think, is the same kind that drove every great human journey before it, the same restlessness, the same refusal to be satisfied by the boundaries of the known world, the same deep, irrational, beautiful hunger to see what's on the other side. But let's come back to the physics again, because there's a fascinating wrinkle we haven't discussed yet, and it fundamentally changes the personal experience of this journey depending on how fast you're going. It's called time dilation, and it is one of the most counterintuitive, reality-bending consequences of Einstein's special theory of relativity. Here's the basic idea. According to special relativity, which has been tested and confirmed to extraordinary precision in countless experiments, time does not pass at the same rate for all observers. Specifically, a clock that is moving relative to you ticks slower than a clock that is stationary relative to you. This isn't a trick, it isn't an illusion or a measurement error, it is a genuine feature of the physical universe. Time itself moves at different rates depending on your velocity, at the speeds of everyday life, driving a car, flying in a plane, even orbiting Earth on the space station. This effect is so tiny it's essentially negligible. Astronauts on the International Space Station age a fraction of a millisecond slower than people on the ground per 6-month mission. Measurable with atomic clocks, utterly insignificant for human experience. But as you approach the speed of light, the effect becomes dramatic, and the mathematics of it, the Lorentz factor, as it's called, describes a relationship where the closer you get to light speed, the more violently time dilates. At 90% of the speed of light, time on the ship passes at roughly 44% the rate it does outside. At 99%, it drops to about 14%. At 99.9%, you're down to about 4.5%. The closer you push, the more extreme the effect, and in principle, at exactly the speed of light, time would stop entirely for the traveler, which is one of the reasons physics doesn't permit objects with mass to actually reach that speed. But here's what this means practically for a light-year journey. If you could somehow accelerate a ship to 99.9% of the speed of light, which would require an almost incomprehensible amount of energy, the journey across 1 light year would take about 1 year, and a few days from the perspective of someone watching from Earth. But from the perspective of the crew inside the ship, it would feel like only about 17 days. To cross a light year, from the outside, just over a year passes. From the inside, just over 2 weeks. Same journey, same distance, 2 completely different experiences of time, both equally real, both equally valid from within their own reference frames. This is not poetry. This is not metaphor. This is verified, measured, experimentally confirmed physics. GPS satellites have to account for time dilation in their calculations, or they'd give you wrong directions within minutes of being switched on. Particle accelerators routinely create particles that should decay in microseconds but last far longer because they're moving so fast that time slows for them. Muons, particles created when cosmic rays hit the upper atmosphere, survive long enough to reach the ground precisely because of time dilation. Without it, they decay kilometers above your head and never arrive. Time dilation is real, and at relativistic speeds approaching the speed of light, it becomes not just real but profound. It becomes the difference between a journey that consumes a civilization and a journey that fits within a single human life. The challenge, of course, is getting there. Getting to 99% of light speed. Getting to a place where time dilation becomes your ally rather than a footnote. And that challenge is where we're headed next, into the specific proposals, the real engineering concepts, the genuine physics that scientists are actively exploring as pathways towards speeds that could make a light year crossable in a human lifetime, because there are ideas out there, serious, peer-reviewed, mathematically grounded ideas, that point toward possibilities most people have never heard of, and some of them are stranger and more wonderful than anything science fiction has dreamed up. That's where we're going in the next section. And I promise you, what's coming will make everything we've covered so far feel like the warm-up. Let's talk about fire for a second, not metaphorical fire. Actual, literal fire, the kind our ancestors first coaxed out of wood and stone somewhere between 1 and 2 million years ago. For an almost incomprehensible stretch of human history, fire was the most powerful energy source available to us. It kept us warm, cooked our food, hardened our tools, and eventually fired the furnaces of the Industrial Revolution. Everything we built for the vast majority of our existence as a species was built on the back of controlled combustion. And then in the 20th century we split the atom. And in doing so, we unlocked an energy source roughly 1,000,000 times more powerful per kilogram of fuel than anything chemical combustion could produce. The entire paradigm shifted. The ceiling of what was energetically possible moved so dramatically that it redefined geopolitics, medicine, industry, and yes, the theoretical limits of space travel. Now here's the question that should immediately follow that thought. If chemistry gave us one level of energy and nuclear fission gave us something 1,000,000 times beyond that, what comes next? What's the next ceiling? And what happens to the problem of crossing a light year when you reach it? The answer might be nuclear fusion. And unlike warp drives or exotic matter, fusion is not theoretical. It is a process that has been running continuously for 4.6 billion years in the star at the center of our solar system. The Sun is a fusion reactor. It fuses hydrogen nuclei into helium, releasing energy according to Einstein's famous relationship between mass and energy. And it has been doing this reliably, continuously, and at extraordinary scale since before the Earth existed. The challenge has always been replicating that process in a controlled way on a human scale, containing a plasma hot enough to sustain fusion, hotter than the core of the Sun itself, using magnetic fields because no physical material can withstand those temperatures. This has been the grand engineering challenge of the late 20th and early 21st centuries. And while we are not there yet in terms of a commercially viable fusion power plant, we are closer than we have ever been. The ITER project, the International Thermonuclear Experimental Reactor, being constructed in southern France, is the largest fusion experiment ever attempted. It is a collaboration between 35 nations representing more than half the world's population. Its goal is to demonstrate that fusion can produce more energy than it consumes, a milestone called ignition, at a scale relevant to power generation. As of the mid-2020s, construction is ongoing, and experiments are scheduled to begin within this decade. But beyond power generation, fusion has a direct application to space propulsion that researchers have been exploring for decades. A concept called the fusion rocket, sometimes discussed under project names like Project Daedalus, a study conducted by the British Interplanetary Society in the 1970s, and more recently Project Icarus, would use controlled fusion reactions to produce exhaust at velocities far beyond what chemical rockets can achieve. The specific impulse, a measure of fuel efficiency in rocketry, of a fusion drive would be orders of magnitude higher than anything we currently operate. Project Daedalus, as designed, was a two-stage unmanned probe intended to reach Barnard's star, about 5.9 light-years away, in roughly 50 years. That implies an average cruise speed of around 12% of the speed of light. 12%. That's not a fantasy number pulled from a science fiction novel. That's the output of a rigorous, multi-year engineering study conducted by actual aerospace engineers working with the physics available to them in the 1970s. At 12% of the speed of light, crossing 1 light-year would take just over 8 years. 8 years. Still a long time by human standards. A child born the day the ship launched would be in secondary school when it arrived, but within a single human lifetime, completable by a person who chose to go, not requiring generations, not requiring descendants to carry the mission forward. One person, 1 lifetime, 1 light-year now. The engineering challenges of a fusion rocket are immense. The fuel requirements for Daedalus were staggering, requiring thousands of tons of helium-3, an isotope rare on Earth, but potentially abundant on the outer planets and their moons. Mining the atmosphere of Jupiter or the surface of the Moon for helium-3 is itself a civilization-scale undertaking, but the physics doesn't forbid it. And that distinction between "we don't know how to do this yet" and "this is physically impossible" is one of the most important distinctions in all of science. But fusion isn't the only unconventional propulsion concept worth discussing. There's another one that sits at the intersection of particle physics and engineering ambition, and it has a name that sounds almost too dramatic to be real. It's called antimatter propulsion. Antimatter is real. It is not science fiction. Every major particle physics laboratory in the world produces it routinely. When a particle collides with its antimatter counterpart, a proton with an antiproton, an electron with a positron, they annihilate each other completely, converting 100% of their combined mass directly into energy. Not the fraction of a percent that fusion achieves, not the tiny fraction of a fraction that chemical combustion achieves. 100%. Total, complete mass-to-energy conversion, exactly as Einstein's equation describes. The energy density of antimatter annihilation is the highest possible energy density that physics permits. Nothing, no process, no reaction, no technology can extract more energy per kilogram of fuel than antimatter annihilation. It is the theoretical ceiling of energy production. A spacecraft powered by antimatter annihilation could, in principle, reach velocities approaching the speed of light. We're talking about the regime where time dilation becomes significant, where the journey that takes years from Earth's perspective might feel like months from the crew's perspective. A ship with an efficient antimatter drive could potentially cross 1 light-year in a time that a single human being could survive and experience meaningfully. The problem, and it is a profound problem, is production and storage. The world's most powerful particle accelerators produce antimatter in quantities measured in nanograms per year. Nanograms, billionths of a gram. To fuel an antimatter rocket capable of reaching relativistic speeds, you would need kilograms, potentially tons, of antimatter. The gap between nanograms and kilograms is not a gap. It is a chasm so vast that even describing it feels almost absurd, and storing antimatter is its own nightmare because the moment it touches ordinary matter, the walls of a container, stray air molecule, anything, it annihilates. You have to suspend it in electromagnetic fields in perfect vacuum with no possibility of contact with anything material, for years, potentially decades of a journey. So antimatter propulsion, while physics permits it, remains far beyond our current engineering capability, not because the idea is wrong, but because the scale of what it requires is simply beyond anything our current civilization can produce or sustain. And yet, here's the thing that I keep coming back to. Every single one of these technologies sits on a continuum. Fusion was theoretically understood in the early 20th century, and we've been engineering toward it for decades. Antimatter was theoretically predicted, then experimentally confirmed, and we now produce it routinely at small scales. The path from theoretically understood to practically achievable is not always short, but it is often real. And the direction of travel in human technological capability has been, over the long arc of history, consistently toward the more energetic, the more efficient, the more capable. We went from fire to fission in roughly 1 million years. We may go from fission to fusion in a century. What comes after fusion, what sits on the other side of that threshold, is something we may not be able to fully imagine yet. Just as a human being sitting by a campfire 100,000 years ago could not have imagined a nuclear reactor. But let's step away from propulsion for a moment and talk about something that almost never gets discussed in this context, something that may actually be more important than the engine, knife negation. How do you navigate across 1 light-year of space? This sounds like it should be simple compared to everything else we've discussed, but it isn't, not even close. On Earth, navigation has become so easy that most people have forgotten it was ever hard. You tap an address into your phone, and a satellite network that took decades and billions to build triangulates your position to within a few meters and draws you a route. It feels effortless. But that effortlessness is the product of extraordinary infrastructure, a global network of carefully maintained, precisely calibrated satellites orbiting at specific altitudes, broadcasting time signals accurate to nanoseconds. In deep space, that infrastructure doesn't exist, and the challenges of knowing where you are, and more importantly, where you're going, across a distance of 1 light-year are genuinely daunting. The most basic navigational tool for interstellar distances is pulsar timing. Pulsars are rapidly rotating neutron stars that emit beams of radio waves with extraordinary regularity. Some of them are so consistent that they rival atomic clocks in their precision. Because different pulsars have different rotational periods and are distributed across the galaxy at known positions, a ship equipped with the right instruments could, in principle, triangulate its position in three-dimensional space by comparing the timing signals from multiple pulsars simultaneously. NASA has actually tested this concept. The Neutron Star Interior Composition Explorer, or NISA, mounted on the International Space Station, successfully demonstrated pulsar-based navigation in 2018. The technology exists, at least in prototype form, but there are complications. At interstellar distances, the positions of stars, including pulsars, shift slightly due to a phenomenon called stellar parallax. The geometry of the galaxy itself introduces drift into any long-duration navigation system, and at relativistic speeds, where time dilation is significant, synchronizing the ship's internal clocks with any external reference becomes a genuinely complex relativistic calculation rather than a simple timestamp comparison. Then there's the question of what you're navigating through. Space, as we mentioned earlier, is not empty. The interstellar medium, the diffuse material between stars, is a mixture of gas, dust, magnetic fields, and radiation. At low speeds, it's largely irrelevant, but at a meaningful fraction of the speed of light, even individual hydrogen atoms become a problem. A ship moving at 20% of the speed of light through the interstellar medium would experience hydrogen atoms as high-energy radiation. Effectively, the ship would be creating its own radiation environment just by moving. The faster you go, the more severe this effect. At very high fractions of light speed, even the sparse interstellar medium becomes a wall of lethal radiation that no current shielding concept adequately addresses. This is called the interstellar medium bombardment problem, and it's one of the less glamorous but deeply serious challenges that any realistic assessment of light-year travel has to contend with. One proposed solution, used in the breakthrough starshot laser sail concept, is to make the ship so small and thin that it presents as an almost negligible cross-section to the interstellar medium. A chip the size of a postage stamp on a sail thinner than a human hair simply doesn't intercept many atoms even at high speed. But that works for a tiny unmanned probe. For a crude vessel of any practical size, carrying people, life support, fuel, food, water, psychology, genetics, culture, the cross-section becomes unavoidable and the bombardment problem becomes acute. There's also something called the bow shock problem. At high enough velocities, a ship moving through the interstellar medium would create a shock wave in front of it, a compression zone where material piles up. Managing, deflecting, or pushing through that shock wave requires energy and engineering that adds yet another layer of complexity to an already extraordinary challenge. And yet, and I mean this sincerely, I don't tell you all of this to discourage. I tell you this because the honest accounting of a problem is the first step towards solving it. Every challenge we've named in this video, radiation, energy, psychology, genetics, navigation, the interstellar medium, is a problem that has been identified, studied, and worked on by real scientists with real tools. The problems are hard. Some of them may take centuries to solve, but none of them have been declared physically impossible. Kai's has not closed the door. Engineering hasn't opened it yet, and somewhere in between those two facts lives the future of human exploration. There's one more concept I want to introduce before we move into the next section, and it's one that most people have never heard of, despite the fact that it sits at the absolute frontier of serious astrophysical thinking. It involves not moving through space at all, but rather using space itself as the vehicle. We touched on the Alcubierre drive earlier. But there's a related concept, arguably even stranger, that deserves its own moment of attention. It's the idea of traversable wormholes. A wormhole, technically called an Einstein-Rosen bridge, is a theoretical connection between two distant points in space-time. Think of it like folding a piece of paper so that two points that were far apart on the flat surface are now touching. The wormhole is the tunnel through the fold. In principle, you could step into one end and emerge from the other, potentially crossing a light year, or 1,000 light years, or 1 billion light years, in an instant. Not quickly, instantly. Einstein and Nathan Rosen first described this mathematical possibility in 1935, working directly from the equations of general relativity. The mathematics genuinely permits these structures. The question is whether they can exist in nature and whether they can be stabilized in a way that allows passage. The short answer, based on current understanding, is we don't know. Unstabilized wormholes, if they form at all, would collapse far too quickly for anything to pass through. Stabilizing one would require, again, exotic matter with negative energy density, the same ingredient that haunts the Alcubierre drive. And as before, negative energies matter is something that appears at the margins of quantum mechanics. The Casimir effect demonstrates that negative energy densities can exist between closely spaced conducting plates, but nothing approaching the quantities needed for a macroscopic wormhole has ever been produced or observed. What's fascinating, and what keeps serious physicists thinking about this, is that in 2022, researchers at the California Institute of Technology and other institutions published work in the journal Nature describing the simulation of a wormhole-like dynamic using a quantum computer. It was a highly simplified, low-dimensional model, not a real wormhole, not a real passage through space, but it demonstrated that the physics of wormhole traversal and certain quantum information phenomena are deeply connected. The research sits at the intersection of quantum gravity, black hole physics, and information theory, some of the most active and exciting frontiers in all of modern science. The universe keeps hinting that there might be more to space and connection than a simple three-dimensional map suggests. It keeps leaving mathematical clues in the equations, structures that look like shortcuts, like bridges, like loopholes in the geometry of reality. Whether any of those clues will ever become engineering is something we genuinely do not know. But here's what I do know. Every generation of humans has looked at the horizon and seen something that the previous generation thought was unreachable. And every generation has eventually found a way to reach it. Not always easily, not always quickly, not always without cost, but consistently, persistently, stubbornly, we reach. 1 light year is today's horizon. It is vast and cold and full of obstacles we haven't fully mapped yet. But it is a horizon, and horizons in the long story of this species have a way of becoming starting points. Now we will step even further back and ask not just how we might cross a light year, but what we might find when we get there, because the destination of that first light year isn't empty space, it isn't a void. And what actually lives in that region of the cosmos, between us and the nearest stars, is something that will genuinely surprise you. Let's do something that most space videos never do. Let's actually go there. Not metaphorically, not in an abstract, hand-wavy, imagine you're in a spaceship kind of way. Let's genuinely try to map what exists, right now, tonight, as you watch this, in the space between Earth and the nearest star. Let's treat that one light year not as an empty corridor, not as a featureless void to be endured, but as a place, a real place, with real structure, real content, real phenomena that science has been slowly, patiently uncovering over the past several decades. Because here's something that doesn't get said often enough. We are not as ignorant of that space as most people assume. We have been studying it, probing it, sending signals into it, and listening for what comes back. And what we've learned, even just in the last 30 years, has fundamentally changed our picture of what the solar neighborhood actually looks like. So, let's start at home and work outward. Right now, as you sit wherever you are, Earth is moving, not just rotating, not just orbiting the Sun. The entire solar system is moving through the galaxy at roughly 220 kilometers per second, orbiting the galactic center on a journey that takes approximately 225 million years to complete. One galactic year. The last time the solar system was in this exact position, in its orbit around the Milky Way, the dominant life form on Earth was a small, mammal-like reptile that had only just survived the greatest mass extinction in the planet's history. The dinosaurs hadn't appeared yet, and as the solar system moves through the galaxy, it moves through a structured environment. The interstellar medium, which we touched on earlier, is not uniform. It has regions of different density, different temperature, different magnetic field strength. Right now, our solar system sits inside something called the local bubble, a region of unusually low density, high temperature gas that extends roughly 1,000 light-years in various directions. The local bubble is thought to have been carved out by a series of supernova explosions that occurred over the past 10 to 20 million years, blowing the denser surrounding gas outward and leaving behind this relatively clear, hot, tenuous region of space within the local bubble. Our solar system occupies an even smaller structure called the local interstellar cloud, sometimes called the local fluff, which is one of the more charming names in all of astrophysics. The local fluff is a warm, partially ionized cloud of gas roughly 30 light-years across, and our solar system has been traveling through it for the past 100,000 years or so. We are somewhere near its edge now, and within the next 10 to 20,000 years, the solar system will likely exit it entirely and enter a different region of interstellar space. This matters for our light-year journey because the conditions inside the local fluff, the density of the gas, the strength of the magnetic fields, the flux of cosmic rays, are subtly different from the open space of the broader local bubble, and different again from what you'd encounter in denser interstellar regions. Any ship traveling outward from Earth would be passing through this structured, layered environment, not through a featureless nothing. Now, let's move outward, past the local fluff, past the boundary where the sun's influence fades, into the territory that sits between us and Alpha Centauri. The first thing you encounter, before you've even left the solar system, technically, is the heliopause. This is the boundary where the solar wind, the constant stream of charged particles flowing outward from the sun, finally loses the battle against the pressure of the interstellar medium. Inside the heliopause, the sun's magnetic field and particle environment dominate. Outside it, interstellar space begins. The heliopause sits at roughly 100 astronomical units from the sun, about 14.9 billion kilometers. Voyager 1, the most distant human-made object ever launched, crossed this boundary in 2012, becoming the first human artifact to enter interstellar space. It took Voyager 1 35 years to get there, moving at about 17 kilometers per second. To put the heliopause in the context of our journey, it sits at roughly 0.0016 light-years from Earth. We're talking about less than 2/1000ths of a single light-year, and it already took our best probe 35 years to reach it. The scale of 1 light-year, measured against our greatest actual achievement in deep space travel, is almost too large to hold in the mind. Beyond the heliopause, the interstellar medium takes over, but it's not empty, and this is where things get genuinely interesting, because sitting out there in the cold, dark space between the heliopause and the nearest stars is one of the most mysterious and poorly understood structures in the entire solar system, the Oort cloud. The Oort cloud is a hypothesized vast spherical shell of icy objects, comets, frozen planetesimals, remnants of the early solar system, that surrounds the Sun at distances ranging from roughly 2,000 astronomical units to perhaps 100,000 astronomical units. That outer edge sits at about 1.6 light-years from Earth, past the midpoint of our journey, almost at the doorstep of Alpha Centauri. Here's the thing about the Oort cloud that stops me every time I think about it. It has never been directly observed. Not a single object has been definitively confirmed to reside in the Oort cloud. We infer its existence from the behavior of long-period comets, objects that arrive in the inner solar system on orbits that suggest they originated in a vast, distant reservoir, perturbed inward by gravitational nudges from passing stars or the tidal forces of the galaxy itself. The mathematics strongly implies the cloud exists, but we have never seen it. Think about that for a moment. There is likely a vast shell-shaped swarm of icy worlds surrounding our solar system, billions of objects, some potentially large enough to qualify as dwarf planets, sitting out there in the dark at distances up to 1.5 light-years from Earth, and we have never directly imaged a single one of them. They are too far away, too cold, too dark. They don't emit light, they barely reflect it. They sit at the very edge of the Sun's gravitational influence, in a cold and silent halo that we know almost entirely through inference and mathematics. A ship traveling from Earth toward Alpha Centauri would, if our models are correct, spend a significant portion of its journey passing through the outer reaches of the Oort cloud. Not a dense field of objects, the Oort cloud is extraordinarily sparse by any local standard, but a diffuse, extended population of icy bodies that represent the solar system's outermost frontier. In a very real sense, you wouldn't truly leave the solar system until you'd cleared the Oort cloud, and clearing it at current spacecraft velocities would take tens of thousands of years. At 12% of light speed, the theoretical maximum of a fusion-driven ship like Project Daedalus, it would still take several years to pass through the estimated extent of the Oort cloud. Years of travel through the solar system's own outer boundary before you'd even begun the journey across the interstellar gap itself. And then, once you're truly clear of the Oort cloud, truly between solar systems in the open interstellar medium, what do you find? More than you'd expect. The interstellar medium in this region contains hydrogen, helium, traces of heavier elements, interstellar dust, tiny solid particles ranging from molecular clusters to grains about a micron across, composed of silicates, carbon compounds and ices. These dust grains are the raw material from which stars and planets form. They carry complex organic molecules, amino acids, the building blocks of proteins, have been detected in meteorites and interstellar clouds. The chemistry of life is not exclusive to Earth or even to planetary surfaces. It happens quietly in the spaces between stars, catalyzed by ultraviolet radiation and cosmic rays on the surfaces of dust grains. over millions of years of slow, patient molecular assembly, this has profound implications. It means that the interstellar medium isn't just background, it's a chemistry lab, a slow-motion, vast, cold chemistry lab that has been running for billions of years and producing molecules that are relevant to the origin of life. The space between stars is not sterile. It is, in a quiet and molecular sense, alive with chemistry. There's also radiation to think about. We mentioned cosmic rays earlier, high-energy particles accelerated to near light speed by supernova remnants, pulsar wind nebulae, and other energetic events scattered across the galaxy. In the interstellar medium, far from the protective magnetic field of any star, cosmic ray flux is higher than it is near Earth. Astronauts on the International Space Station in low Earth orbit are partially shielded by Earth's magnetic field. Astronauts on the Moon receive significantly more radiation exposure. Astronauts in deep space, beyond Earth's magnetosphere, beyond the solar wind's partial protection, receive more still, and in the interstellar medium, shielded only by whatever the ship itself can provide. The radiation environment is harsher again. This isn't an insurmountable problem. Thick water shielding, polyethylene, and other hydrogen-rich materials are effective at blocking many forms of radiation, and the ship's structure itself provides some protection, but it's a constant, cumulative hazard, a biological reality of the journey that can't be engineered away entirely, only managed and mitigated now. Let's talk about what actually waits at the end of one light year, or rather, what lies in the general direction of the nearest stars and what we've learned about it in recent years. Because this is where astronomy has delivered some of the most extraordinary surprises of the 21st century. Alpha Centauri, 4.24 light-years away at its closest component, Proxima Centauri, the nearest stellar system to our own, and as of 2016 we know it hosts at least one confirmed planet, Proxima Centauri b, a world orbiting in the habitable zone of Proxima Centauri, the region where liquid water could theoretically exist on the surface. It's roughly Earth-sized. It orbits its star in just 11 Earth days because Proxima is a red dwarf, a small, cool, dim star, and the habitable zone sits much closer in than it does around a star like our Sun. Whether Proxima b is actually habitable is a genuinely open question. Red dwarfs are known for producing intense stellar flares, sudden eruptions of radiation and charged particles that can be orders of magnitude more powerful than anything our Sun produces. A planet orbiting as close as Proxima b would be subjected to these flares on a regular basis, whether it retains a thick enough atmosphere to shield its surface, whether it has a strong enough magnetic field to deflect the charged particles, whether the tidal forces of orbiting so close to its star have left it geologically active or geologically dead. These are all questions we cannot yet answer. But here's what matters. It's there, a planet, around the nearest star. Within one light year of the solar system's neighborhood, in cosmic terms essentially next door, there is at least one world that sits in the right zone for liquid water. And if the universe has taught us anything, it's that where liquid water is possible, the question of life is not absurd. There may also be more planets around Proxima Centauri. A candidate called Proxima c has been proposed, and the data are still being refined. And the Alpha Centauri A and B system, the two Sun-like stars that orbit each other in the same triple system, may also host planets, though confirming their existence has proven difficult due to the complexity of looking for small signals around binary stars. The point is this: one light year isn't just a journey through empty space toward empty space. It's a journey through a structured, layered, chemically active, physically rich environment, the outer solar system, the hypothetical Oort cloud, the interstellar medium, toward a stellar neighborhood that we now have concrete reason to believe contains worlds, actual worlds, potentially complex, potentially surprising worlds. The destination isn't an abstraction, it's a place. And when you frame the question that way, not how long would it take to travel 1 light year through empty nothing, but how long would it take to reach the nearest known exoplanet system, something in the question changes. It becomes heavier, more urgent, more real. It also makes the timescales we've been discussing feel different. Because when we say it would take our current best spacecraft 73,000 years to cover 1 light year, we're saying it would take 73,000 years to reach a star system that may contain a living world. 73,000 years to potentially answer, one way or another, the oldest question humanity has ever asked: are we alone? That question deserves more than an aside. It deserves its own moment. Because the proximity of Proxima Centauri b, the fact that the nearest potentially habitable world sits within the very range of distance we've been discussing, transforms the technical problem of light-year travel into something with genuine existential stakes. If we solve the propulsion problem, if fusion drives or antimatter engines or something we haven't thought of yet bring crossing times down to decades or centuries rather than millennia, we don't just get to explore. We get to potentially answer the question, the one that has haunted every civilization, every religion, every philosophy, every human being who has ever looked up at a clear night sky and felt the weight of the dark. We could go there, we could look, and whether we found a barren rock, a world covered in microbial mats, or something we have no conceptual framework to describe, any of those answers would be the most significant discovery in the history of our species, unambiguously, irreversibly, permanently. No other scientific result in human history would compare, and it sits at the end of 1 light year that currently takes our best hardware 73,000 years to cross. 1 light year that could potentially be crossed in 8 to 10 years with fusion propulsion that we haven't built yet, but that physics doesn't forbid. 1 light year that sits between us and a question that may have been asked since the first human being looked up and wondered. I want you to sit with that for a moment, not the engineering, not the timelines, just the stakes, because now we're going to bring all of this together in a way that I think will genuinely shift how you see our moment in history. The story of 1 light year doesn't end with a problem. It ends with a choice, and that choice is closer than you think. Let's talk about a moment in history that most people have completely forgotten. 1492. Christopher Columbus set sail from the port of Palos de la Frontera in southern Spain with 3 ships, roughly 90 men, and a navigation theory that was frankly wrong in several important ways. He believed the Earth was smaller than it actually is. He underestimated the distance to Asia. He had no idea an entire pair of continents stood between him and his destination. By any rigorous modern standard of pre-mission planning, the voyage was built on a foundation of significant miscalculation. And yet he went, and the world changed forever. Not because Columbus was right about the details. He wasn't. Not because the mission went exactly as planned. It didn't. But because the act of going, of committing resources, lives, and institutional will to crossing an unknown ocean produced consequences that no one involved could have predicted or fully imagined. The world that existed after 1492 was categorically different from the world that existed before it. Not better in every way. The consequences of that contact were devastating for the peoples already living in the Americas, but different, irreversibly, permanently, categorically different. History has a structure, and that structure, if you look at it honestly, tends to hinge not on moments when everything was perfectly understood, but on moments when someone chose to move despite the uncertainty, despite incomplete knowledge, despite genuine risk. Now, I'm not suggesting we launch an interstellar mission tomorrow. with fusion drives we haven't built and navigation systems we're still designing. The analogy isn't meant to be literal, but I want to use it to ask a different kind of question than the ones we've been asking so far. Not how long would it take? We've covered that thoroughly. The answer, depending on the technology, ranges from 73,000 years with current hardware to 8 to 10 years with theoretical fusion propulsion, with a vast landscape of intermediate possibilities between those extremes. The more interesting question, the one that actually determines what happens next, is this: when do we decide to start? Because here's something that doesn't get discussed enough in the context of interstellar travel. The problem is not just technological. It's not just a matter of waiting until the engineering catches up with the physics. There's a third dimension to the challenge that is in some ways more difficult than either the physics or the engineering, because it operates on timescales and through mechanisms that are fundamentally human rather than scientific. The problem is civilizational will. What does it take for a civilization to commit, genuinely commit, over the span of generations, with sustained funding and institutional focus and cultural priority, to a goal that will not be achieved within the lifetime of anyone alive at the moment of commitment? Think about what that actually means. The people who vote to fund an interstellar mission will never see the result. The engineers who design the propulsion system will never see it tested at full scale. The astronauts, or the people whose descendants become the astronauts, may not even be born yet. The entire endeavor requires a kind of multi-generational contract that modern democratic societies, built on 4- and 5-year political cycles and quarterly earnings reports, are structurally very poor at making. We have managed it before in limited ways. The construction of medieval cathedrals in Europe took generations. The architects who laid the foundations knew they would not live to see the spires completed, and they built anyway. The long-term management of nuclear waste requires institutions and warning systems designed to communicate danger to people living 10,000 years from now, who may not speak any language currently in use. These are examples of civilizational thinking that extends beyond individual lifetimes, but interstellar travel would require this kind of thinking at a scale and duration that dwarfs anything we've attempted. Not decades, not centuries, potentially millennia of sustained commitment, depending on the propulsion technology ultimately available. Unless, and this is where the 21st century introduces something genuinely new into the equation, the nature of what we are as a civilization changes in ways that make this kind of long-term commitment more tractable. Artificial intelligence is the obvious candidate, not the narrow AI systems we use today to recommend videos and filter spam, but the trajectory that field is on, towards systems capable of sustained, autonomous, long-duration planning and execution at scales no human institution can match. An AI-managed interstellar mission, one where the decision-making, course correction, scientific analysis, and mission adaptation over decades or centuries of flight is handled by systems that don't age, don't lose institutional memory when a key person retires, and don't require a budget renewal every fiscal year, changes the calculus dramatically. This isn't science fiction speculation. The Breakthrough Starshot initiative, the laser sail concept aiming to send a gram-scale probe to Alpha Centauri at 20% of light speed, is explicitly designed around autonomous operation. The probe would be too far away for meaningful real-time communication. Signals take over 4 years to make a one-way trip at light speed, so every decision the probe makes during its journey and arrival must be handled autonomously. The human mission controllers on Earth would be setting intentions, not giving instructions. The mission itself would be run by the machine. Extend that logic to a crewed mission, or even a more sophisticated robotic one, and you start to see how artificial intelligence doesn't just assist interstellar travel, it may be the enabling condition for it. Not because humans can't be brave or committed enough, but because the timescales involved are simply beyond what unaided human institutions have historically been able to sustain. There's another factor that's worth naming directly, because it sits underneath almost every conversation about the future of space exploration, even when it isn't explicitly discussed. Climate. The state of Earth's biosphere over the coming centuries will have a profound effect on whether humanity has the collective bandwidth, the resources, the stability, the institutional capacity, the sheer cultural energy to pursue goals as ambitious and long-horizon as interstellar exploration. A civilization in crisis, managing cascading environmental emergencies, mass migrations, food system disruptions, and the geopolitical instability that comes with all of those things, is a civilization that tends to focus its energies on survival rather than exploration. This is not a pessimistic point. It is a structural one. The history of exploration is largely the history of societies that had enough stability and surplus, enough security in the immediate term to invest in the uncertain long term. The great ages of exploration tended to follow, not precede, periods of social and economic consolidation. They required a foundation. Earth's ability to provide that foundation over the coming centuries, as the climate system responds to the carbon we've already emitted, as the global population continues to grow and then potentially stabilize, as renewable energy transitions reshape economies and geopolitics, will be one of the determining factors in whether interstellar exploration remains a dream or becomes a plan. None of this is beyond our influence. Every decision made by every person and institution and government alive today about energy, emissions, consumption, and technology ripples forward into the future in ways that are genuinely consequential. The people who will one day decide to build the first interstellar ship, or who will decide not to, haven't been born yet, but the world they inherit is being shaped right now. I want to shift gears one more time, because there's an angle on this story that almost never gets told, and I think it's the most human one of all. Throughout this video, we've talked about crossing 1 light year as a problem. A physics problem, an engineering problem, a biology problem, a psychology problem, a civilizational problem, and it is all of those things. But I want to suggest that it's also something else. It's a mirror. The question, how long would it take to travel 1 light year, is, in disguise, a question about what we are, what we're capable of, what we prioritize, what we're willing to endure, what we're willing to imagine, what we're willing to begin even knowing we won't finish. Every answer we've explored in this video. From the honest despair of 73,000 years at current speeds, to the cautious optimism of fusion propulsion, to the wild theoretical hope of warp geometry or wormhole topology, every answer reflects something about the species asking the question. Our current technology reflects our current values and investments. Our theoretical concepts reflect the reach of our imagination. Our inability to sustain multi-generational commitments reflects something real about how we've organized ourselves, and our persistent, recurring return to the question, the fact that humans keep asking it, keep writing about it, keep building the physics and the engineering around it, even when the timescales are daunting, reflects something real about our nature too. We are the species that ask the question. That alone is remarkable. Think about every other species that has ever lived on this planet. 5 billion species approximately over the 4 billion year history of life on Earth. 5 billion lines of biological experiment, most of which ended in extinction before producing anything that looked up at a night sky and wondered what was out there. The vast majority of life on Earth has been, and remains, concerned exclusively with the immediate, food, safety, reproduction, the next moment. Evolution is ruthlessly short-sighted. It builds for survival, not for curiosity. And yet here we are, a species that evolved on the savannas of Africa for reasons entirely unrelated to astronomy, looking at points of light that take years to reach at the speed of light, the highest speed permitted by the universe, and not just noting them but obsessing over them, spending careers studying them, spending billions building telescopes to examine them in finer detail, spending the energy and ingenuity of our greatest minds on the question of how we might one day go there. That is not something evolution required of us. It is something we added, something we became, somewhere along the way, that goes beyond the strict biological mandate. And whatever you want to call that quality, curiosity, wonder, ambition, the will to explore, it is, I would argue, the most distinctly human thing about us. More than language, more than tool use, more than social complexity, the reach toward the genuinely unreachable, the refusal to accept the horizon as a boundary rather than a beginning. 1 light-year sits at the edge of what we can currently reach. And like every horizon our species has ever faced, it is simultaneously a measure of how far we have to go and a testament to how far we've already come. Because let's be honest about where we started. 100,000 years ago, we couldn't reliably cross an ocean. We didn't know what was on the other side of the horizon line where the water met the sky. We were small, vulnerable, short-lived creatures with stone tools and fire, huddled against the dark on a rocky planet orbiting an unremarkable star on the edge of a galaxy we had no concept of. And in that 100,000 years, a single blink in geological time, a rounding error in cosmic time, we have worked out the age of the universe. We have mapped the large-scale structure of the cosmos. We have detected gravitational waves from colliding black holes 1 billion light-years away. We have photographed the shadow of a supermassive black hole 65 million light-years distant. We have landed machines on Mars, floated a helicopter in its atmosphere, and listened to the sound of Martian wind through a microphone. We have sent a machine beyond the boundary of our own solar system and received signals from it across 14 billion kilometers of space. We did all of that, starting from stone tools and fire. The distance between where we started and where we are now, measured not in kilometers but in capability, in knowledge, in reach, is arguably greater than the distance between where we are now and a ship capable of crossing 1 light-year in a human lifetime, arguably. And that thought, more than any specific propulsion concept or theoretical shortcut, is what I find most genuinely inspiring about this question. Not the warp drives, not the wormholes, not even the fusion rockets, but the trajectory, the direction of travel. The fact that the arrow of human capability across the broad sweep of our history has consistently pointed outward. We don't know exactly when the first light year will be crossed. We don't know by whom or with what technology, or whether they will be biological humans or something descended from us. We don't know what they will find when they get there, or what that discovery will mean for everything that comes after. But we know the question will keep being asked. We know the physics will keep being worked. We know the engineering will keep advancing. And we know, because history says so clearly, that the distance between this is impossible and this is done has a way of collapsing faster than anyone predicted. Whenever a civilization decides that something truly matters, 1 light year, tonight, when it gets dark wherever you are, go outside. Let your eyes adjust for a few minutes. Look up. Find the brightest star you can see in the southern sky if you're in the southern hemisphere, or look for the familiar patterns if you're in the north. Every single point of light you can see with your naked eye is within a few thousand light-years of Earth, cosmic neighbors in the grand scheme of things. The nearest of them, Alpha Centauri, is invisible from most of the northern hemisphere but blazes in southern skies, a brilliant point of light that looks, to the naked eye, like a single star, but is actually a triple system, one component of which may harbor a world. That light left its source 4 years ago. It has been traveling toward your eye since before you started watching this video. It carries information, not metaphorically, but literally, encoded in its spectrum and intensity, about the physical conditions of a star system that may include a planet capable of supporting liquid water. You can see it with your naked eye, without a telescope, without any technology at all, just eyes and darkness, and somewhere in the physics and mathematics and imagination of our species, there is a path from that naked eye observation to actually going there. We haven't walked it yet, but we know it exists. We're going to explore something that I think is the final, crucial piece of this puzzle, the one variable that ties together the propulsion and the biology and the psychology and the civilizational will and the philosophical weight of the question: time itself. Not travel time, not how long the journey takes in years and decades, but the nature of time as a physical phenomenon, what relativity really means for the experience of crossing 1 light year, and why the universe has, hidden inside its own laws, something that might be the most extraordinary gift it could have given to any species ambitious enough to use it. The universe, it turns out, may have built a loophole into the very fabric of reality, and it has your name on it. If you're still watching, your mind works the way this channel was built for. Don't forget to subscribe and give this video a like. Every video we take a real question about the cosmos and follow it all the way down. No shortcuts, no fluff, just wonder. Let's start with something that sounds like it belongs in a philosophy lecture rather than a physics one. Time is not what you think it is, not even close. The version of time that feels obvious and intuitive, the steady, reliable, universal clock ticking at the same rate for everyone everywhere, is a fiction. A useful fiction, one that works perfectly well for the speeds and scales of everyday human life, but a fiction nonetheless. The universe does not run on a single clock. It never did. And the moment you start moving at speeds that are a meaningful fraction of the speed of light, the gap between the intuitive version of time and the actual version becomes not just measurable but profound. We touched on this earlier in the series. But I want to go deeper now, because time dilation isn't just a curiosity or a footnote in the story of interstellar travel. It is potentially the most important physical phenomenon in the entire conversation. It changes the question we've been asking, fundamentally, structurally, from the ground up, and the implications reach far beyond physics into philosophy, ethics, and the very meaning of what it would mean for a human being to cross 1 light year. So let's build this carefully. Let's make sure it lands properly. Albert Einstein published his special theory of relativity in 1905. He was 26 years old, working as a patent clerk in Bern, Switzerland, and he was in the process of dismantling several of the most fundamental assumptions in physics, assumptions that had stood unquestioned for over 200 years. One of those assumptions was the universality of time, what Einstein showed through a combination of thought experiments, mathematical reasoning, and a willingness to follow the logic wherever it led, even when it defied common sense, was that time is not a fixed background against which events happen. Time is a dimension woven together with the 3 dimensions of space into a single 4-dimensional fabric called space-time. And just as space can be curved, stretched and compressed by mass and energy, time can be stretched and compressed by motion and gravity. The specific effect we care about here is called time dilation due to velocity. It works like this. The speed of light, roughly 300,000 kilometers per second, is the same for every observer in every reference frame, regardless of their own motion. This is one of the foundational postulates of special relativity, and it has been confirmed by every experiment ever designed to test it. It is, as far as we can tell, an absolute law of the universe, Now, if the speed of light is constant for everyone, then something else has to give when observers are moving relative to each other. That something is time. Specifically, a clock carried by a moving object ticks more slowly than a clock at rest, and the faster the object moves, the more pronounced the effect at ordinary speeds. The speeds of cars, aeroplanes, even rockets, the effect is real but minuscule. A commercial airliner flying for 12 hours accumulates a time dilation of a few nanoseconds relative to someone on the ground. GPS satellites, moving faster and at higher altitude, have to correct for time dilation effects in their onboard clocks, or they would gradually drift out of sync and become useless for navigation. The effect is real, measurable, and actively engineered around in modern technology. But at speeds approaching the speed of light, the effect stops being a minor correction and becomes dramatic, world-altering, reality-reshaping. Let me give you the numbers because they're extraordinary. At 10% of light speed, roughly 30,000 kilometers per second, time dilation is relatively modest. For every year that passes on the ship, about 1 year and half a day passes on Earth. Barely noticeable at 50% of light speed, the gap widens. For every year on the ship, about 1 year and 2 months pass on Earth. Still manageable. At 90% of light speed, things start getting genuinely strange. For every year experienced by the crew, roughly 2 years and 3 months pass on Earth. At 99% of light speed, 99%, the numbers become surreal. For every year on the ship, about 7 years pass on Earth. At 99.9%, 99.9, it's 22 years on Earth for every year on board. At 99.999%, 5 nines, it's approximately 700 years on Earth for every year on the ship. And as you approach ever closer to 100%, to light speed itself, the ratio approaches infinity. The ship's clock approaches a standstill relative to the outside universe. Time for the traveler effectively stops now. What does this mean for our 1 light-year journey? Here is where the loophole lives. 1 light-year, by definition, is the distance light travels in 1 year. So light, moving at 100% of light speed, covers 1 light-year in 1 year. For a photon, a particle of light, there is no experience of time at all. The journey from here to Alpha Centauri, 4.24 light-years away, takes 0 subjective time from the photon's perspective. It doesn't age, it doesn't experience duration, it simply departs and arrives. A ship can't move at exactly light speed. That's physically forbidden for anything with mass, as we've discussed. But a ship can move arbitrarily close to light speed, given enough energy. And as it does, the ratio of ship time to Earth time becomes increasingly favorable for the crew. Consider a ship accelerating at 1 gravity, the same gravitational pull you feel right now sitting wherever you are, which happens to be about the most comfortable, sustained acceleration for a human body. For the first half of the journey, then decelerating at 1 gravity for the second half to arrive at the destination at a manageable speed. This constant 1 gravity acceleration profile is often used in thought experiments about interstellar travel because it solves 2 problems simultaneously. It provides propulsion, and it provides artificial gravity for the crew through the acceleration itself. Under this profile, the crew would reach 50% of light speed after about 6 weeks of travel. They'd reach 90% after about 6 months. At 1 gravity of continuous acceleration, the ship approaches light speed asymptotically, getting closer and closer, but never quite reaching it. Now run the numbers for a journey to Proxima Centauri, 4.24 light-years away. Under constant 1 gravity acceleration and deceleration, Earth time for the journey, approximately 5.9 years. Ship time experienced by the crew, approximately 3.6 years. To the crew, the journey to the nearest star takes about 3.5 years of lived experience, not a generation, not a lifetime. 3.5 years, less time than a typical university degree, and it gets more dramatic the further you go, because time dilation compounds as speed increases. Longer journeys at the same acceleration profile don't scale linearly in ship time the way they do in Earth time. For a journey to the center of the Milky Way, roughly 26,000 light-years from Earth, Earth time would be approximately 26,000 years. But ship time, under continuous one-gravity acceleration and deceleration, would be about 21 years, a single human lifetime. You could, in principle, travel from Earth to the galactic center and back within a human lifespan, while 26,000 years elapsed on Earth each way. Let that settle for a moment. The galaxy is not too large for a human being to cross in terms of personal experience time. It is too large in terms of the energy required, and in terms of the relationship between the traveler and anyone left behind. But the universe does not impose a hard biological limit based on distance alone. It imposes a limit based on energy and on the strange, poignant asymmetry that time dilation creates between the traveler and the world they left. And that asymmetry is where the philosophy lives. Imagine you board an interstellar ship at age 30. You make the journey to Proxima Centauri under the one-gravity profile we described. You spend 3.5 years in transit. You arrive, spend some time, let's say a year, examining the system, collecting data, doing science that changes everything humanity thought it knew. Then you make the return journey. Another 3.5 years as you arrive back at Earth at age 39, 9 years older, broadly speaking, by your own biological clock, but Earth time has passed differently. While you experienced 9 years of ship time, approximately 12 years have elapsed on Earth. The friends and family you left behind are 12 years older. If you had a child who was 5 when you left, they are now 17, not 9, 17. That gap, that quiet, irreversible divergence between your experienced time and the world's elapsed time is one of the most poignant consequences of relativistic travel, and it deepens dramatically for longer journeys. If you were to make a trip to a star 100 light-years away, something that might be crossed in decades at sufficiently high velocity, you might return to Earth to find that a century has passed. Everyone you knew is gone. The world has changed in ways you can't predict or prepare for. You return to a civilization that has moved on without you. The ancient myth of Rip Van Winkle, the man who falls asleep for 20 years and wakes to find the world transformed, takes on a new dimension in the context of relativistic travel. Except in this version, Rip Van Winkle chose to go. He chose the journey. He accepted the terms. And the question becomes, what would motivate a person to make that choice? To trade their place in the living present for the possibility of reaching somewhere extraordinary, knowing that the world they return to will not be the world they left? The answer, probably, is the same thing that has motivated explorers throughout human history. Not indifference to what they're leaving behind, but a love of what lies ahead that is larger than the fear of loss, the pull of the unknown, the need to know what's there. Some people are simply made that way, and history suggests they always will be. But there's another layer to this that is specifically relevant to our 1 light-year question, and it's a layer that doesn't get discussed often enough. Time dilation is not just a gift to the traveler, it's also a potential asset for the mission. Here's what I mean. One of the central problems of any interstellar journey, and we've discussed this at length, is the biological endurance of the crew. The human body is not designed for decades of continuous exposure to microgravity, radiation, social isolation, and the psychological weight of a journey with no return visible on the horizon. The longer the trip in experienced time, the more the biological and psychological challenges compound. But if time dilation compresses the experienced duration of the journey, if a 50-year Earth time crossing can be accomplished in 5 years of ship time through relativistic velocity, then many of those challenges become more tractable, not trivial, not solved, but more manageable. The question shifts from how do we keep a crew healthy and sane for 50 years to how do we keep a crew healthy and sane for 5 years. And while 5 years in deep space is still a genuinely difficult problem, it is not obviously insurmountable in the way that 50 years is. This is why serious physicists and mission planners who think about interstellar travel tend to regard time dilation not as a strange side effect to be noted and moved past, but as a core feature of the solution space. The universe's own rules applied at sufficient velocity do some of the heavy lifting. Of course, the energy cost of reaching those velocities is the counterbalancing reality. To push a crewed ship, something massive enough to carry life support, radiation shielding, food, water, recycling systems, medical equipment, science instruments, and the physical and psychological infrastructure for a human crew, to 99% of light speed requires energy that dwarfs anything our current or near-future civilization can produce. The Lorentz factor, the mathematical expression of how time dilation scales with velocity, is generous with time compression but brutal with energy demands. The closer you push to light speed, the more energy each additional fraction of a percent costs. On a curve that approaches infinity at the limit, this is why the breakthrough Starshot concept uses gram-scale probes rather than crewed ships. At gram scale, the energy required to reach 20% of light speed via laser sail is at least theoretically achievable with near-future technology. A crewed ship at the same velocity requires orders of magnitude more energy, and at 99% of light speed, where time dilation really starts doing dramatic work, the energy requirements are currently beyond anything we can seriously plan for. But here's the thing about energy. The history of human civilization is in many ways the history of our relationship with energy. Stone Age humans commanded the energy of their own muscles and the fire from burning wood. The Industrial Revolution added coal and steam. The 20th century added petroleum, natural gas, and nuclear fission. Each transition unlocked capabilities that the previous era would have considered impossible. Not difficult, impossible, a civilization that has mastered fusion power, and we are arguably closer to that than we have ever been, with facilities like ITER under construction and private fusion companies achieving milestones that would have seemed impossible a decade ago, commands energy at a scale that makes interplanetary travel routine and interstellar travel at least theoretically imaginable. A civilization that has mastered antimatter production and storage, still well beyond us, but not forbidden by physics, commands energy at a scale where relativistic interstellar travel becomes genuinely conceivable. The energy ladder is real. We are on it. We have been climbing it for our entire history as a species, and each rung we ascend opens possibilities that the previous rung couldn't reach. Now I want to bring together every thread we've pulled on across this entire video: the propulsion, the biology, the psychology, the interstellar environment, the destination, the civilizational will, the philosophy of exploration, and now the physics of time itself, and ask the question that ties them all together. Given everything we know, everything we've built, everything we're building, and everything we can at least coherently imagine, what is the most honest, most grounded, most intellectually rigorous answer to the question, how long would it actually take to travel 1 light year? The answer is not a single number. It can't be, because the answer depends on when you're asking, what technology you're using, and, crucially, whose clock you're reading. With the technology we have right now, today, in the year this video was made, approximately 73,000 years, that's the honest baseline. No shortcuts, no future breakthroughs, just our actual existing hardware applied to the actual distance. With near-future technology, ion drive scaled up, solar sails, nuclear pulse propulsion of the Orion variety, we might get that down to 10 to 20,000 years. Still civilizationally catastrophic for any crewed mission. Manageable, perhaps, for robotic probes carrying information rather than life. With fusion propulsion, the kind Project Daedalus and its successor Project Icarus modeled, crossing times to Alpha Centauri dropped to 40 to 50 years of ship time, or somewhat less depending on the specific design. 1 light year in perhaps 8 to 12 years of ship time at the velocities fusion enables within a human career. Challenging but conceivable for a crewed mission, given the right life support and psychological infrastructure. With antimatter propulsion, hypothetical, energy-intensive, but physically coherent, relativistic velocities become achievable, and time dilation starts doing real work. 1 light year in experienced ship time could drop to a year or less, depending on the velocity achieved. The energy cost is staggering by current standards. By the standards of a mature Type II civilization on the Kardashev scale, one harnessing the full energy output of its star, it becomes conceivable. And with hypothetical space-time geometry manipulation, Alcubierre drives or traversable wormholes, the question of travel time in the conventional sense becomes almost moot. These concepts bypass the speed limit entirely rather than approaching it asymptotically. Whether they're physically realizable remains genuinely unknown. But here's the answer I keep coming back to, the one that feels most true. 1 light year would take exactly as long as we decide it takes, not in a motivational poster, anything is possible kind of way, in a precise technical, historically grounded kind of way. The timeline from our current 73,000-year baseline to a crossing time measured in human lifetimes is determined not primarily by the laws of physics, which are, as we've seen, surprisingly permissive, but by the choices our civilization makes, about energy research, about space investment, about the kind of long-horizon thinking our institutions are capable of sustaining, about whether we treat the question as a fantasy or as an engineering problem. Kosygins has given us the runway. The runway is real, the physics works. What happens next, whether we taxi out onto that runway and begin to accelerate, is up to us. And that, I think, is both the most humbling and the most empowering thing this question can teach us. We are not passengers in the story of our own reach into the cosmos. We are, in the most literal sense, the authors of what happens next. 1 light year, the universe put it there, within sight, within theoretical reach, just far enough away to require us to become something greater than we currently are, and just close enough to remain, against all odds, a realistic destination rather than a permanent dream. Because it turns out that 1 light year is simultaneously one of the most daunting distances the human mind has ever confronted, and one of the smallest meaningful distances in the universe. Both of those things are true at once, and holding both of them in your mind at the same time is, I think, the most accurate way to see where we stand. Let me give you a number that I want you to really sit with for a moment. 93 billion, that's the diameter of the observable universe, measured in light years. 93 billion light years from one edge to the other, the full span of everything we can, even in principle, detect. Every galaxy, every star, every planet, every black hole, every wisp of gas and dust that has ever emitted or reflected light in the 13.8 billion years since the Big Bang, all of it contained within that sphere, 93 billion light-years across. 1 light-year is 1/93 billionth of that distance. If the observable universe were scaled down to the size of Earth, roughly 12,700 kilometers in diameter, 1 light-year would be about 137 micrometers. That's roughly the diameter of a single human hair, maybe slightly thinner depending on the hair. The distance we have spent this entire video wrestling with the distance that requires our most advanced theoretical propulsion concepts, that demands biological engineering and psychological innovation and civilizational commitment across generations, is, on the scale of the actual universe, thinner than a hair across the surface of a sphere the size of our planet. Let that land. And before you feel deflated by that, before the sheer scale of the cosmos makes the challenge feel not just daunting but absurd, I want to offer you the opposite interpretation. Because the same fact that makes 1 light-year feel microscopic also makes it feel precious, significant, worth every ounce of effort we could possibly direct toward it. Here's why. The universe is not uniformly distributed. It is not a smooth, homogeneous soup of matter spread evenly across 93 billion light-years of space. It is instead organized into a hierarchy of structures, each nested within the next, each with its own characteristic scale and its own relationship to the question of what eachable means for a species like ours. Let's climb that hierarchy together, starting from where we are. Earth sits, as we've established, about 8 light minutes from the Sun. The Sun is a star. Our solar system, the full extent of it, including the Oort cloud, the distant halo of icy bodies that forms the outermost gravitational boundary of the Sun's influence, extends roughly 1 to 2 light-years from the Sun in all directions. So 1 light-year puts you squarely within the Sun's own extended neighborhood, not at another star, not even most of the way to another star, within the diffuse outer reaches of the system you were born in. The nearest star to the Sun, Proxima Centauri, the red dwarf we've mentioned repeatedly, is 4.24 light-years away. The Alpha Centauri triple system, of which Proxima is the most distant member, is about 4.37 light-years. The next nearest stellar neighbor, Barnard's star, is about 5.96 light-years. Beyond that, Wolf 359 at 7.8 light-years, Lalande 21185 at 8.3, and so on, a scattering of stellar neighbors, each separated from the next by gaps of several light-years. This region, the volume of space within about 15 or 20 light-years of the Sun, is what astronomers sometimes call the solar neighborhood. It contains roughly 50 to 60 known stars and brown dwarfs within 15 light-years, and the density is broadly typical of the Milky Way's disk in our region, not crowded, not sparse, just the ordinary texture of the galaxy in our corner of it. The Milky Way itself, the galaxy we live in, is roughly 100,000 light-years in diameter, with a thickness of about 1,000 light-years in the disk, where most of the stars live, and a central bulge that swells to perhaps 15,000 light-years thick. It contains somewhere between 100 billion and 400 billion stars. The exact number is uncertain because dust clouds in the galactic plane obscure our view of large portions of the disk, and counting stars behind a dust cloud is like trying to count people in a stadium through a frosted window. You can estimate, but precision is elusive. Our solar system sits about 26,000 light-years from the galactic center, about halfway out from the core toward the edge of the disk, embedded in a minor spiral feature called the Orion Arm. We orbit the galactic center at roughly 220 kilometers per second, a speed that sounds impressive until you realize it still takes the solar system about 225 to 250 million years to complete one full orbit. The last time we were in roughly this position in our galactic orbit, the dominant land animals on Earth were the earliest dinosaurs. Beyond the Milky Way, the next major structure is the local group, the gravitationally bound family of galaxies to which the Milky Way belongs. The local group contains more than 50 known galaxies, though most are small dwarf galaxies. The two largest are the Milky Way and the Andromeda Galaxy, also known as Messier 31. Andromeda is currently about 2.5 million light-years away and is moving toward us at roughly 110 kilometers per second. In approximately 4.5 billion years, the two galaxies will begin a slow, complex merger, a process that will take another few billion years to complete and will reshape both galaxies fundamentally, though the stars themselves are so widely spaced that direct stellar collisions will be extraordinarily rare. The local group itself is part of the Virgo supercluster, a vast assemblage of galaxy groups and clusters centered on the Virgo cluster, about 54 million light-years away. The Virgo supercluster spans roughly 110 million light-years, and even that structure is just one lobe of a larger structure called Laniakea, a supercluster of superclusters identified in 2014 that spans roughly 500 million light-years and contains the mass of approximately 100 million billion suns. And Laniakea is one of countless such structures scattered across the observable universe, which contains, at best estimate, roughly 2 trillion galaxies in total, 2 trillion galaxies, each containing, on average, hundreds of billions of stars, each of those stars potentially accompanied by planets. And we are, right now, sitting on one of those planets watching this video, trying to figure out how to cross 1 light year. I am not sharing these numbers to make you feel small, though it's difficult to sit with them and not feel at least a little bit small. I'm sharing them because I think the scale of the cosmos is directly relevant to the question we've been asking in a way that isn't always made explicit. Here it is, the relevant point. The universe is almost incomprehensibly large, and it is, as far as we currently know, almost incomprehensibly empty of the specific thing we're looking for: other minds, other beings capable of asking the same questions we ask, other civilizations wrestling with the same problems, looking at the same kind of night sky, wondering the same things about the lights above them. The Fermi paradox, named after the physicist Enrico Fermi, who reportedly asked the question over lunch in 1950, captures this tension precisely. Given the age of the universe, given the number of stars, given the seemingly reasonable assumption that at least some fraction of them host planets with life that eventually evolves intelligence, the galaxy should, by some calculations, be teeming with technological civilizations. At least some of them should be old enough to have spread across the galaxy in the time available. So where are they? The silence is, genuinely, one of the most profound puzzles in science. And it has generated dozens of proposed explanations, some optimistic, some deeply sobering. Maybe intelligence is far rarer than we assume. Maybe the emergence of complex multicellular life, nervous systems, language, and technology is not a probable outcome of biological evolution, but a staggeringly improbable one, a series of lucky accidents that happened once, here, and almost nowhere else. Maybe civilizations tend to destroy themselves before they develop interstellar capability through war, environmental catastrophe, the misuse of powerful technologies, or simply the social and political challenges of sustaining long-term civilizational coherence. Maybe interstellar travel is simply harder than it looks even at the theoretical level, that there are physical or engineering barriers we haven't yet identified that make crossing the gaps between stars not just difficult but functionally impossible, even for advanced civilizations. Maybe the signals are there and we're not listening in the right way or on the right frequencies or with sensitive enough instruments. Maybe interstellar travel takes so long, even for advanced civilizations, that the galaxy appears empty simply because no one has had time to cross it yet, that we are, in cosmic terms, early, that the story is just beginning, and the universe is mostly a stage that hasn't yet been filled. Each of these possibilities, if true, carries enormous implications for what we should do and how urgently we should do it, and none of them can be definitively ruled out with our current knowledge. But here's what I find most striking about the Fermi paradox. in the context of our journey. Whether the silence around us reflects the rarity of intelligence, the difficulty of interstellar travel, the self-destructive tendencies of technological civilizations, or simply the vast timescales involved, in every one of those scenarios, what we do next matters enormously. If we are rare, then our survival and eventual expansion into the cosmos is not just a human priority but arguably a cosmic one. We may be among a very small number of minds in the observable universe, and the question of whether we thrive or fail carries weight that extends far beyond our solar system. If civilizations tend to self-destruct, then every year we survive as a technological species without tearing ourselves apart is a small victory for the possibility of intelligence persisting long enough to reach the stars. Every generation that maintains the knowledge base, the social structures, the institutional memory, and the scientific tradition that makes interstellar capability conceivable is a generation that moves the needle. If interstellar travel is harder than it looks, then the work being done right now, the fusion research, the propulsion experiments, the theoretical physics, the robotic missions to the outer solar system, the planning documents that won't bear fruit for centuries, is exactly the kind of work that eventually, in ways we can't predict, cracks the problem. That's how every apparently impossible problem in the history of technology has been solved. Not in a single breakthrough, but in a cascade of incremental advances, each building on the last until one day someone looks up and realizes the barrier is gone. And if we are simply early, if the universe is a stage in the process of filling and we are among the first acts, then the responsibility is, if anything, the most exhilarating of all. Because it means the story is not written, the galaxy is not spoken for, the billion-year narrative of intelligence spreading through the cosmos has not yet been authored, and we, this species on this planet at this moment, are astonishingly in the position of being among its first writers 1 light year. In the context of all of this, it's not just a distance, it's a threshold, the first step beyond the immediate neighborhood of our own star, the first proof, if we cross it, that the barriers are not absolute, that the gaps between stars are not walls but doors, that the universe, for all its indifference to us as individuals, has not made itself unreachable. Now I want to talk about something that I think represents, in some ways, the most underappreciated development in the history of humanity's relationship with interstellar space. And it doesn't involve rockets or lasers or warp drives, it involves radio waves. In 1974, astronomers using the Arecibo radio telescope in Puerto Rico beamed a message into space. The Arecibo message, designed by Frank Drake and Carl Sagan, was a binary encoded transmission containing basic information about humanity, our mathematics, our biology, our solar system, our physical form. It was aimed at the globular cluster Messier 13, roughly 25,000 light-years away. A message in a bottle, flung into the cosmic ocean. It will take 25,000 years to arrive. The reply, if one is ever sent, will take another 25,000 years to reach us. No one alive today will ever know if the message was received, but the act of sending it was not, I think, primarily a practical strategy for making contact. It was something else. It was a declaration, a statement, made in the language of mathematics, the only language that might be truly universal, that we are here, we are thinking, we know you might be out there, and we refuse to stay silent just because the distances are vast. We reached out across 25,000 light-years with the tools of 1974. Not physically, not yet, but informationally, at the speed of light, the fastest speed the universe permits, in the most durable and universal format we could devise. That's not nothing. In a universe that may be profoundly empty of minds, the act of one mind reaching toward another, even across distances that dwarf anything we've discussed in this video, even with no expectation of response within any human lifetime, is in some ways the most important thing we've ever done. We have been sending radio signals into space inadvertently since the early 20th century. Every radio broadcast, every television transmission, every radar pulse has been leaking outward from Earth at the speed of light for over 100 years. By now, a sphere of human radio noise roughly 200 light-years in radius surrounds our solar system, expanding outward at light speed into the galaxy. Any civilization within 200 light-years of Earth that has radio receivers and is paying attention has, at least in principle, had the opportunity to notice us. 200 light-years is a tiny fraction of the galaxy's 100,000 light-year diameter. We are a whisper at the edge of a vast and mostly silent auditorium, but the whisper is real. It's out there, moving outward at 300,000 kilometers per second, carrying fragments of every radio drama, every television comedy, every military radar ping, every weather satellite transmission humanity has ever produced. A strange, chaotic, unintentional autobiography of a civilization just beginning to find its voice, and somewhere, in the physics of that expanding sphere of signal, is something I find quietly magnificent. Every photon in that sphere, every quantum of radio energy spreading outward from Earth, left our planet as a result of human intention, human ingenuity, human creativity, or human necessity. Every one of them carries, in however indirect and encoded a form, the fingerprint of minds, of consciousness, of the fact that on this planet, at this moment in cosmic time, something woke up and started talking. That's what 1 light-year means. In its deepest sense, it's the distance at which the conversation starts. It's the point past which our signals have already reached. Our unintentional broadcasts have passed the 1 light-year mark roughly a century ago and continue outward. Our intentional transmissions like the Arecibo message blazed past it in seconds. In the electromagnetic sense, the sense of information and signal and reach, we have already crossed 1 light-year many times over, in every direction simultaneously at the highest speed the universe allows. What we haven't done yet is send ourselves, our physical selves, our biology, our presence. We've sent our words and our mathematics and our radar noise, but not a single human atom has ever crossed even a tiny fraction of 1 light-year beyond Earth. That gap between the reach of our signals and the reach of our bodies is the frontier we're actually talking about. And it is, in the end, a gap not between us and the stars, but between who we are now and who we might become. Let's talk about what's actually happening right now, not in science fiction, not in theoretical papers sitting in academic journals that nobody outside of a university physics department will ever read, not in the optimistic projections of futurists who have been promising flying cars and moon colonies since the 1960s. I mean right now, on this planet, in this decade, with real money, real engineers, real hardware, and real results. Because one of the most frustrating things about conversations around interstellar travel is the assumption, often unspoken, rarely examined, that it belongs entirely to the future, that it's the kind of topic you file under maybe someday, and then get on with your life. That the gap between where we are and where we'd need to be is so vast that nothing happening today is meaningfully connected to the goal of crossing 1 light-year. That assumption is wrong. And I want to show you exactly why. Let's start with propulsion, because propulsion is, in the most literal sense, the engine of this conversation. The most important near-term development in advanced propulsion is happening not at NASA or the European Space Agency, but in the world of nuclear fusion, specifically the race to achieve what physicists call ignition. Fusion ignition is the point at which a fusion reaction produces more energy than was required to initiate it. For decades, this milestone seemed perpetually just around the corner. The running joke in physics was that fusion was always 30 years away, no matter what year you were standing in. Then, in December 2022, the National Ignition Facility at Lawrence Livermore National Laboratory in California announced that they had achieved fusion ignition for the first time in history. A laser system delivering 2.05 megajoules of energy to a tiny capsule of hydrogen fuel produced 3.15 megajoules of fusion energy, a gain factor of about 1.5. The output exceeded the input. Ignition achieved. Now, to be precise about what this does and doesn't mean, the total energy budget of the experiment, including the energy required to power the lasers themselves, was far larger than the fusion output. The experiment was a scientific milestone, not a demonstration of a working power plant, but scientific milestones are exactly how technologies begin. The first controlled fission reaction, achieved by Enrico Fermi's team at the University of Chicago in 1942, was similarly a proof of principle rather than a power station. Within 13 years, the first commercial nuclear power plant was operating. The fusion ignition result at Livermore has since been repeated and improved upon. Private fusion companies, including Commonwealth Fusion Systems, TE Technologies, Hillian Energy, and several others, have raised billions of dollars in investment and are pursuing parallel paths to fusion power using different confinement and fuel approaches. Commonwealth Fusion's Spark Tokamak, under construction in Massachusetts, is targeting first plasma in the mid-2020s and is designed to achieve significant net energy gain using high-temperature superconducting magnets that represent a genuine engineering breakthrough. Why does this matter for interstellar travel? Because fusion propulsion, the kind that Project Daedalus modeled in the 1970s and Project Icarus has been refining ever since, requires exactly the kind of high-gain, sustained fusion reactions that ignition makes possible. A fusion rocket isn't the same as a fusion power plant, but the underlying physics overlap substantially. Progress in one domain accelerates progress in the other. Every breakthrough in fusion confinement, fuel efficiency, and energy gain is a step, however indirect, toward the propulsion systems that could carry a probe and eventually a crew toward the nearest stars. Now let's talk about something even more immediate, something with hardware already built and a launch date already set: the Dragonfly mission. Dragonfly is a NASA mission to Titan, the largest moon of Saturn and one of the most scientifically extraordinary objects in the solar system. Titan has a dense nitrogen atmosphere, liquid methane lakes and rivers on its surface, complex organic chemistry, and conditions that some researchers believe might be relevant to the question of how life originates. Dragonfly is a rotorcraft lander, essentially a drone the size of a small car that will fly through Titan's thick atmosphere, hopping between sites to sample surface materials and measure chemical composition. Now, Dragonfly isn't going to cross 1 light-year. It's not even leaving our solar system, but it matters in this conversation for a reason that has nothing to do with distance. Dragonfly represents the leading edge of a new generation of autonomous, capable, long-duration robotic exploration systems. The navigation, decision-making, power management, and communication architecture being developed for Dragonfly, operating in an environment where radio signals take over an hour to travel from Earth, making real-time control impossible, is directly relevant to the kind of autonomy that any interstellar probe would need. A probe crossing even 1 light-year would be out of communication range for a year per signal round trip. It needs to think for itself, make decisions, prioritize objectives, and handle failures without waiting for instructions from Earth. Dragonfly is, among other things, a school for that kind of independence. Similarly, the Voyager probes, launched in 1977, have now crossed into interstellar space. Voyager 1, the most distant human-made object ever built, is currently more than 23 billion kilometers from the Sun. It crossed the heliopause, the boundary where the Sun's solar wind gives way to the interstellar medium, in 2012. For over a decade now, it has been operating in genuine interstellar space, transmitting data back to Earth on a power budget smaller than a refrigerator light bulb, managed by onboard computers with less processing power than a modern digital watch. Voyager 1 is traveling at approximately 17 kilometers per second. At that speed, it would take roughly 73,000 years to cross 1 light year. We know this, we've said it many times. But what Voyager represents, in terms of what it has taught us and what it continues to teach us, is worth appreciating independently of its velocity. It has told us what the interstellar medium actually feels like from the inside, rather than from observations made safely within the heliosphere. It has measured the plasma density, the magnetic field orientation, the particle environment of the space between stars, data that directly informs the design challenges any future interstellar probe will face. It is right now a working scientific instrument operating in the environment we want to reach, sending back information at the speed of light that is genuinely irreplaceable. And it was launched with 1970s technology. Imagine what we could do with what we know now. Let's talk about laser sails, because this is where the most exciting and most concrete near-term work on interstellar relevant propulsion is happening. Breakthrough Starshot, the initiative announced in 2016 by physicist Stephen Hawking, investor Yuri Milner, and Facebook founder Mark Zuckerberg, proposed using a ground-based laser array to accelerate gram-scale spacecraft to 20% of the speed of light. At that velocity, a probe could reach Alpha Centauri in roughly 20 years. The engineering challenges are formidable. The laser array would need to deliver gigawatts of power in tightly focused beams over enormous distances. The sail material needs to be extraordinarily thin, highly reflective, and capable of surviving both the intense laser pulse and the bombardment of interstellar dust particles at 20% of light speed. The onboard electronics need to fit within a gram or less of mass and survive the acceleration, the radiation environment, and the journey of 20+ years. The communication system needs to transmit data across 4 light years on essentially no power. None of these problems are solved. But here's what's important. None of these problems are obviously unsolvable. They're engineering problems, hard ones, genuinely, seriously hard ones. But physics does not forbid the solutions. They're not like the energy problem for crude relativistic ships, where the numbers border on the absurd even for advanced civilizations. They're in the category of difficult but conceivable with sufficient investment and time. Breakthrough Starshot has been funding research into the specific sub-problems since its announcement. Researchers have been working on ultra-thin light sail materials, high-power laser systems, chip-scale spacecraft design, and the atmospheric compensation needed to keep a laser beam focused over planetary distances. Progress has been real if incremental. The timescale for a demonstration mission, not a full interstellar shot, but a proof-of-concept laser sail test, is measured in decades, not centuries. Meanwhile, the European Space Agency and NASA have both been developing and testing solar sails, large, thin reflective membranes that use the gentle pressure of sunlight rather than a laser for propulsion. Solar sails can't reach anywhere near 20% of light speed. Sunlight is far too gentle for that, but they're testing the fundamental technologies of thin film deployment, attitude control, and pressure-based navigation that laser sail missions would build on. The Japanese Ikaro's mission, launched in 2010, was the first spacecraft to demonstrate sustained solar sail propulsion in deep space. NASA's Advanced Composite Solar Sail System, launched in 2024, is testing improved sail materials and deployment mechanisms. Each of these missions is a brick in a wall that is, slowly and unevenly but genuinely being built. Let's shift to something that often gets overlooked in conversations about interstellar travel because it doesn't involve propulsion at all. It involves biology. One of the hardest problems in any long-duration space mission isn't engineering. It's keeping human bodies functional and human minds intact over timescales that evolution never prepared us for. The human body was designed, by billions of years of natural selection, to operate at one gravity, within a magnetic field that deflects most harmful radiation, with regular cycles of light and dark, within complex social environments of dozens to hundreds of individuals, with access to nutritionally diverse food, and with the psychological comfort of knowing that the ground beneath your feet is an essentially infinite resource and that help in some form is never very far away. Remove all of those conditions, as spaceflight does, and the body and mind begin to respond in ways that are sometimes predictable and sometimes surprising and rarely helpful. The International Space Station has been continuously occupied since November 2000, giving us over 2 decades of data on what long-duration spaceflight does to human physiology. The results are in some ways more encouraging than early worst-case projections, and in other ways more complicated. Bone density loss in microgravity is real but manageable with the right exercise protocols. Astronauts on the ISS spend roughly 2 hours a day on resistance and aerobic exercise specifically to counteract it. Muscle atrophy follows similar patterns, vision changes, caused by fluid shifts in the body increasing pressure on the optic nerve. A condition called spaceflight-associated neuroocular syndrome remain one of the more worrying and not fully understood findings, with some astronauts experiencing lasting vision changes after long missions. Radiation exposure is a serious concern. The ISS sits within Earth's magnetosphere, which provides significant shielding. Beyond that protection, in deep space, on a journey to Mars or further, cosmic ray exposure increases dramatically. Long-term elevated radiation exposure raises cancer risk and may have neurological effects, including cognitive impairment. Current NASA guidelines limit career radiation exposure for astronauts, and those limits would be exceeded by a Mars mission of typical duration, let alone anything reaching toward the stars. Psychological health over long-duration missions is an active research area. Studies of analog environments, Antarctic winter-over stations, submarine deployments, isolated habitat simulations show that confinement, monotony, interpersonal friction, communication delays with loved ones, and the absence of novelty and sensory diversity all impose real psychological costs. These are manageable for months. For years, the challenges compound in ways that current research is still mapping. But here's what's genuinely encouraging. Every one of these biological challenges is a known problem. We know about bone loss, and we have countermeasures. We know about radiation, and we have shielding strategies, pharmaceutical interventions being developed, and, for ships accelerating at 1 gravity, the possibility of using artificial gravity to address several issues simultaneously. We know about psychological strain, and we have selection criteria, interpersonal training, mission design strategies, and mental health support systems being developed specifically for long-duration missions. This is how medicine works. You identify the problem, you study it, you develop countermeasures, you test them, you refine them. We are right now in the identify and study phase for most of these challenges. The countermeasures are coming. The CHAPIA missions, crew health and performance exploration analog, conducted by NASA, involve volunteers living in a simulated Mars habitat on Earth for a full year, testing not just psychological responses but also food production, resource management, communication delays, and the social dynamics of a small, isolated crew. The first mission ran in 2023 and 2024, The data from these missions directly informs the design of future long-duration deep space missions. Meanwhile, in a development that might sound like science fiction but is firmly in the domain of real and active research, the field of synthetic biology is beginning to address some of the most fundamental biological barriers to long-duration spaceflight. Researchers are exploring genetic modifications that might enhance radiation resistance in human cells, drawing inspiration from organisms like Deinococcus radiodurans, a bacterium that can survive radiation doses thousands of times higher than would kill a human being by virtue of extraordinarily efficient DNA repair mechanisms. The idea is not to make humans into bacteria, but to understand and eventually transfer some of the underlying molecular machinery. Similarly, research into suspended animation, or more precisely, therapeutic hypothermia and metabolic suppression, has advanced substantially in medical contexts where inducing controlled hypothermia in patients has been used to protect the brain during cardiac surgery and after cardiac arrest. The gap between therapeutic hypothermia in a clinical setting and the kind of long-duration metabolic suppression that might allow a crew to effectively sleep through an interstellar journey is enormous. But it is not a gap between science and science fiction. It's a gap between early-stage capability and mature capability. Those gaps close, given time and attention. Let me give you one more development that I find particularly striking because it addresses a problem we haven't discussed as explicitly as it deserves. Navigation. How do you know where you are in interstellar space? On Earth, we have GPS, a network of satellites that triangulates position by measuring the time delay of radio signals. In the inner solar system, NASA's Deep Space Network provides navigation by tracking the Doppler shift of radio signals from spacecraft, measuring how the signal frequency changes as the spacecraft moves, and integrating that over time to determine position and velocity with remarkable precision. Voyager 1's position is known to within kilometers, despite being over 23 billion kilometers away, precisely because of this technique. But beyond the solar system, the Deep Space Network's signals become too faint to be useful for navigation at the precision required. You need a different approach. Pulsar navigation, sometimes called XNav, is a proposed solution that turns the galaxy's natural infrastructure into a GPS system. Pulsars are rapidly rotating neutron stars that emit beams of radiation with extraordinary regularity, some of them keeping time to better than 1 part in 10 to the power of 15, which makes them more precise timekeepers than the best atomic clocks on Earth. By measuring the arrival times of pulsar signals from multiple known pulsars simultaneously, a spacecraft can triangulate its position anywhere in the galaxy to within a few kilometers. NASA has already demonstrated a version of this technology on the International Space Station using an instrument called NISA, the Neutron Star Interior Composition Explorer, to show that pulsar-based navigation is feasible with current detector technology. The precision achieved in the demonstration was within 10 kilometers, not yet sufficient for all navigational purposes, but proof that the concept works. An interstellar probe equipped with a pulsar navigation system would, in principle, always know exactly where it was, anywhere in the galaxy, without needing to communicate with Earth. It would navigate by the stars themselves, not their visible light, but their rhythmic, precise, galaxy-spanning radio heartbeats. There's something poetic about that. Using the most extreme stellar remnants in the universe, the collapsed cores of dead stars, spinning hundreds of times per second, broadcasting their existence across thousands of light years. As the navigational beacons for humanity's first steps toward the stars, the universe, it turns out, has been building our GPS system for billions of years. We just had to learn to read it. All of these developments, fusion ignition, laser sail research, long-duration biology studies, pulsar navigation are pieces of a puzzle that is genuinely being assembled right now by real people working on real problems with real tools. None of them individually gets us across 1 light year, but each of them closes a gap. Each of them converts a theoretical problem into an engineering challenge, or an engineering challenge into a solved design question, or a solved design question into a demonstrated capability. That's how impossible things become possible, not in a single flash of inspiration, but in a long, patient, often unglamorous accumulation of incremental progress, each step building on the last, until the destination that once seemed unreachable is suddenly, undeniably within reach. We are not there yet. But we are building. We started this journey with a single question. How long would it actually take to travel 1 light year? And I want to answer it now. Not with a dodge, not with a "it depends," not with a list of caveats that leaves you feeling like you never really got a straight response. I'm going to give you the most honest, most complete answer I can. Because you've earned it. You've sat through the physics and the biology and the philosophy and the engineering and the history, and you deserve a real answer. So, here it is. With the fastest spacecraft humanity has ever built, the Parker Solar Probe, which reached a peak speed of around 692,000 kilometers per hour during its close solar approaches, it would take approximately 6,900 years to travel 1 light year. That's roughly the time separating us from the earliest known writing systems of ancient Mesopotamia, multiplied by more than 2. Civilizations would rise and fall several times over in the course of that journey. The probe would arrive in a galaxy that had changed, around a star that might have changed, to deliver data to a civilization that would be utterly unrecognizable to the people who launched it. With ion propulsion, the most fuel-efficient drive technology currently flying in operational spacecraft, travel times to 1 light-year range from roughly tens of thousands to hundreds of thousands of years, depending on the specific system, the available power source, and whether you can sustain continuous thrust. Dawn, Hayabusa, and their successors are marvels of efficiency. They are not remotely interstellar. With a nuclear pulse drive of the Orion concept, the theoretical spacecraft that would have ridden a rapid series of nuclear explosions to perhaps 3 to 5% of light speed, the journey across 1 light year would take somewhere between 20 and 33,000 years. Still enormous, still beyond any individual human scale, but beginning at least to shift from geological time towards something that a species might theoretically plan for. With a fusion rocket of the Daedalus or Icarus class, sustained fusion propulsion achieving perhaps 12% of light speed, 1 light year falls in roughly 8 to 9 years of travel time. That's a human timescale, that's a career, that's a childhood to early adulthood. 8 or 9 years and you're there. The engineering required is immense, the fuel requirements are staggering, and we are probably a century or more away from building such a system. But 8 or 9 years is a number a human being can hold in their hands. With an antimatter rocket operating at the theoretical limits of current physics, achieving perhaps 50 to 80% of light speed, 1 light year could be crossed in roughly 1 to 2 years of ship time, with relativistic effects beginning to compress that further as velocity increases. Antimatter propulsion at scale is not a technology we have. It may be one we never have, given the extraordinary difficulty of producing and storing antimatter in macroscopic quantities, but the physics is real, the ceiling exists, and it's a ceiling a human being could live beneath. With a laser sail system of the breakthrough starshot variety, tiny probes accelerated to 20% of light speed by a ground-based laser array, the crossing takes about 5 years, no crew, no life support, a chip-scale spacecraft the mass of a paperclip, but 5 years to 1 light year is by any measure a number that begins to make interstellar space feel not close, never close, but not impossibly far, and at full relativistic speed, as close to the speed of light as physics permits, driven by a hypothetical propulsion system we don't yet have any idea how to build. 1 light-year could be crossed in something approaching 1 year of ship time, with the outside universe aging rather more. At 99.9% of light speed, ship time for a 1 light-year journey would be roughly 16 days. Not a commute, but not an epoch either. Those are the numbers. Clean, honest, and grounded in real physics rather than speculation. But the numbers, as I hope the last 9 parts have made clear, are not really the point. The point is what they represent. The slowest figure, 6,900 years with our fastest current spacecraft, tells you where we are. It tells you that we are, right now, at the absolute beginning of the interstellar story. Not the middle, not the early chapters, the first sentence, in the beginning of a narrative that will take thousands of years to fully unfold, assuming we survive and maintain the will to pursue it. The fastest figure, days of ship time at near light speed, tells you where the physics allows us to go. It tells you that the universe has not made itself unreachable by the laws it operates under. It has made itself very hard to reach, brutally, almost mockingly hard, but not physically forbidden. The ceiling is high, inconceivably high from where we stand, but it is a ceiling, not a wall. And the figures in between, 8 years with fusion, 5 years with laser sails, tell you something perhaps most important of all. They tell you that the gap between where we are and where the physics allows us to go is not empty, it's full of engineering problems being worked on right now, full of physics being explored, full of technologies being funded and tested and refined, full of human beings who have chosen as their life's work to make those numbers smaller. The journey of 1 light year is not a journey across space. Not really. It's a journey across time, the time it takes for a species to grow from its first tentative steps off its home planet to the point where the stars are genuinely within reach. We are somewhere in the early stages of that journey. We don't know how long it will take in total. We don't know if we'll make it. There are no guarantees. History is littered with civilizations that collapsed before they reached their potential, and we have no reason to assume we're immune to that fate. But we are moving. Let me tell you something about the nature of exponential progress, because I think it's the most important single concept for understanding where we stand in this story. For most of human history, progress was slow. The gap between the technology of one generation and the technology of the next was often imperceptible. A farmer in ancient Mesopotamia would have found the tools of a farmer 500 years later broadly familiar. A Roman engineer would have recognized most of the construction methods used in medieval Europe. Change happened, but it happened slowly enough that individual human lives were lived almost entirely within the context of a single technological era. That changed in the Industrial Revolution, and then it changed again in the 20th century, and the rate of change has been accelerating with occasional pauses and setbacks ever since. Consider this. In 1903, the Wright brothers achieved the first powered, controlled, sustained heavier-than-air flight at Kitty Hawk, North Carolina. Their flyer covered a distance of 37 meters in 12 seconds. 66 years later, within a single human lifetime, Neil Armstrong stepped onto the surface of the Moon. The distance from the surface of Earth to the surface of the Moon is roughly 384,000 kilometers. In 66 years, the range of human flight increased by a factor of roughly 10 billion. 10 billion times in 66 years. That is what exponential technological progress looks like. And it doesn't require any magical thinking or unfounded optimism to observe it. It's the documented historical record. Now, interstellar travel is harder than getting to the Moon. enormously harder. The moon is 1.3 light seconds away. 1 light year is, as we've established, a distance so much larger that the comparison is almost comical. I'm not suggesting we'll reach the stars in 66 years or 660 years. I'm not making a specific prediction at all, because specific predictions about technology timescales are almost always wrong, usually in the direction of underestimating how long things take in the near term and overestimating how long they take in the long term. What I am saying is that the same underlying dynamic, the compounding, accelerating accumulation of scientific knowledge and engineering capability that took us from 37 meters in 12 seconds to the surface of the moon in 66 years, is still operating. It hasn't stopped. It hasn't reversed. If anything, the pace of scientific publication, the global connectivity of research communities, the computational tools available for modeling and simulation, and the financial resources flowing into frontier science and technology are all larger than they've ever been before. The problems between us and 1 light year are real. I want to be honest about that. They're not trivial. Some of them may require breakthroughs that don't follow predictably from anything we currently know. But they are the kind of problems that the compounding engine of human scientific progress eats for breakfast over sufficient time. And there's something else worth saying. Something about the relationship between the goal and the journey. Every technology developed in the pursuit of interstellar capability will have applications that reach far beyond interstellar travel itself. Fusion power, whether developed primarily for energy or for propulsion, would transform the global energy economy and address climate change in ways that could extend the habitability of our planet by centuries. Advanced closed-loop life support systems designed for generation ships would have direct applications in sustainable agriculture, water management, and ecological engineering on Earth. Radiation shielding and biological countermeasures developed for deep space missions would advance cancer treatment and radiation medicine. Pulsar navigation would provide a GPS-independent positioning system for spacecraft throughout the solar system. Autonomous AI systems designed for probes operating light years from Earth would advance robotics. Healthcare and infrastructure management here at home. The pursuit of the stars makes us better at living on this planet. It always has. The technologies we use every day, from satellite communications to water purification, to scratch-resistant lenses, to memory foam, to the digital image sensors in your phone, trace their origins, directly or indirectly, back to the space programs of the 20th century. The investment in reaching outward has always returned value inward. That's not an accident. It's the nature of ambitious goals. They pull you forward, and in the pulling, they develop you. They stretch your capabilities in directions you didn't anticipate. And those unexpected directions turn out to be valuable in ways you couldn't have predicted when you set the goal. Reaching for 1 light year will make us better at being human, regardless of whether we ever physically cross that distance. The reaching itself has value. Now I want to talk about legacy, about the relationship between the people alive today and the people who will one day, if we are lucky and wise and persistent enough, stand on the threshold of interstellar space and take that first step beyond the solar neighborhood. The people who will build the first genuine interstellar probe, whether it's a laser-propelled chip-scale craft or a fusion-powered robotic explorer or something we haven't imagined yet, are, statistically speaking, probably already alive. Some of them are children right now. Some of them are teenagers. Some of them are young researchers, fresh out of graduate school, working on problems that seem only distantly related to interstellar travel, plasma physics, materials science, artificial intelligence, molecular biology, without necessarily knowing that the work they're doing is laying foundations for something that will, in a century or two, change the course of human history. They will build on work being done today. And the people doing work today built on work done decades ago. And the people who did that work built on foundations laid by others before them, stretching back through centuries of patient, cumulative scientific effort. Science is, in this sense, the longest collaboration in human history. A conversation across generations, conducted in the language of mathematics and experiment, in which each participant inherits the accumulated wisdom of everyone who came before and adds their own contribution to the edifice, and then hands it, enlarged and deepened, to whoever comes next. You are part of that conversation, not in spite of the fact that you're watching a video about space, rather than working in a physics laboratory, but because of it. Understanding is the foundation of caring. Caring is the foundation of supporting. Supporting is the foundation of funding, of voting for science budgets, of encouraging the young people in your life who show an interest in these questions, of choosing to live in a way that takes seriously the long-term survival and flourishing of the species. The people who will one day cross 1 light year will need a civilization behind them, a civilization that believes it's worth doing, a civilization that has maintained across generations the institutional memory, the scientific tradition, the economic capacity, and the collective will to pursue a goal that yields its fruit on timescales longer than any individual human life. That civilization is built, person by person, generation by generation, out of exactly the kind of curiosity and wonder and willingness to engage with big questions that brought you to this video. You matter to this story, not as a passenger but as a participant. Let me end with an image, not a graph or a formula or a comparative table. An image. It is night. You are standing outside, somewhere away from city lights, in a field, on a hillside, on a beach, and the sky above you is clear. The Milky Way stretches overhead in a broad, faintly luminous band, billions of stars so densely packed that from this distance they blend into a soft, continuous glow. You can see, if you know where to look, the faint smudge of the Andromeda Galaxy. 2.5 million light-years away, visible to the naked eye on a clear night, the most distant thing your unassisted eyes can see. And somewhere in that sky, in the direction of the constellation Centaurus in the southern hemisphere, where the 2 bright stars of Alpha Centauri mark the nearest stellar system to our own, there is a point of light, faint, unspectacular, easily lost among thousands of other stars. Proxima Centauri, 4.24 light-years away. 1 light-year is a quarter of that distance. Less between you and that faint point of light lies everything we've talked about. The 9.46 trillion kilometers, the radiation and the cold and the microgravity and the micrometeorites, the fusion reactions and the laser pulses and the antimatter and the relativistic time dilation, the generation ships and the hibernation pods and the pulsar navigation and the autonomous artificial intelligence, the civilizational will and the philosophical reckoning and the cascade of compounding technological progress, all of it contained in the space between where you're standing and that point of light. And you, standing there looking up at it, you are made of atoms forged in stellar interiors. Your carbon was cooked in the core of a star that lived and died before our sun was born. Your oxygen, your iron, your calcium, all of it stellar. You are, in the most literal physical sense, a child of the stars, and you are looking at them and wondering and asking how long it would take to go back. That impulse, that wondering, that asking, is not a distraction from the serious business of living. It is not a luxury or an indulgence. It is the deepest expression of what you are, a mind assembled from stellar material, awakened to consciousness, and turned in its moments of clarity toward the cosmos that made it. The stars are not indifferent to us, because indifference requires us awareness. and the stars don't have awareness. But the cosmos that produced them also produced us. The same physics, the same chemistry, the same long patient cascade of cause and effect, operating across 13.8 billion years. We are not separate from the universe, we are an expression of it. The universe in us, looking at itself 1 light year. That's the distance to the next room in the house the cosmos built. We'll get there, not today, not in our lifetimes, but we'll get there because that's what we do. That's what we've always done. We look at the horizon and we decide the horizon is not the end, it's the beginning of somewhere else. And then we build whatever we need to build to cross it. The question was never really how long it would take. The question was always whether we would try, and we will, we always do. But before you go, if this blew your mind, the next video will shatter it. Click on the video on your screen right now to explore the real reason interstellar travel is impossible. Because everything we just talked about, there's a wall that stops all of it. A hard, physical, terrifying wall, and you need to see it.